Who's the chair? Can I start? No chair. Okay. So my talk from neurotech to fintech is including.
Yeah. All right. So. Good morning, everyone. So we continue our journey in different areas of mathematics. So we are very pleased to have Mina Tasher from University of Miami, who is going to tell us what all she knows about neurotech and fintech.
Thank you very much. And it's an honor to speak in the inauguration conference of this center. From neurotech to fintech, I'm going just to give small introduction to put it in place, and then zoom, not zoom like we're doing now, but zoom like focus on complex system, and then the mathematics that we need, and then finally from neurotech to fintech. So in the introduction, I just say that the brain and the financial markets are two examples that together with cities and transportations and health systems and atmosphere and the ocean, they are all complex systems. So we move from neurotech to fintech through the study of a general complex system and through basic observation into the brain and financial market. So the talk should have been from neurotech to fintech via complex system, because there is also a neurofinance field, which is a totally different approach. So what is a complex system? It's not easy to define. There is a popular characterization, which means it's a collection of individuals whose behavior affect the total in a way which is unclear to the observer. So the popular characterization, it doesn't say what is a complex system, it says what it is not. It's unclear and of course very personal what is unclear and which observer. But in terms of a collection of individuals, the brain is formed out of neurons, financial markets traders, social system usually people, molecules of atoms, and the weather is formed of airflows. So there is a new study, complex system study, which investigates now more precisely how parts give rise to the collective behavior of the whole, and how the parts are interacting with each other, and also how the system relates to the environment. So it's a very interdisciplinary, multidisciplinary, transdisciplinary, cross-disciplinary, because it's across all traditional disciplines. Of course, math in the first, in the headline, but then physics, biology, as well as engineering, management, medicine, and social sciences. So this for the introduction. And now we do a little bit of a zoom. So there is a possible to make a definition. So a complex system is a collection of individual entities. Different systems have different individual entities, that the behavior is influencing the dynamic of the entire system. And also the interaction between the particles is influencing the dynamic system, but in a non-linear fashion. And external actions can modify individual behavior from the outside. And of course, we'll see that both in the neuroscience and in financial market, that individual neuron is affecting by things that happen outside of the body, and a trader is influenced by rumors or different issues. And the collective behavior is self-organized. So all these phenomena satisfied in the neural networks, in dynamic population, in medicine. They became so popular during COVID. Global warming, transportation system, migration of people, public health management, global trading, cities, and the internet, of course, is a big complex system. And studying complex system is challenging. Why is it challenging? First of all, indirect effects are challenging in general, but here it's really extremely mysterious. Causes and effects are not obviously related. And pushing on a complex system here often has effects over there, because the parts are interdependent. So this, the butterfly syndrome is something that you can think of extreme as pushing here and getting result over there. And there is also uncertainty. So uncertainty is challenging because the objects, why uncertain? The objects are not well defined. In a certain collection, we say these are the objects, but there's so much on the periphery and the boundary. The rules of operation are not identified. They combine different scales, address different level of hierarchy, and involves deterministic as well as stochastic aspects. And it's also unpredictable. And this is challenging. If there is self-organization is always difficult to control or not to control. The external actions are globally non-predictable, and sudden unpredictable collective deviation from usual behavior can occur. So an extreme such unpredictable event, even with rational and controlled individual behavior, is called the black swan. So 2008, what happened in the market in 2008, the collapse is referred to nowadays already as a black swan, something unpredictable, totally unpredictable. And this is my contribution from neurotech to fintech, identify a black swan. So mathematics in complex system study. Why do we have to look on method complex system? Well, when you see all the challenges before, what but mathematics can solve such challenges? So certainly
I have a question.
Already?
I feel that the definition of complex system doesn't have much. It sounds like describing just our world.
You want to say the world is a complex system?
Yeah.
Yeah, that's true. But like we have a group and we have subgroup, the world is a complex system, but inside we have also sub-complex systems, which are complex systems by themselves. Of course, you can look at everything as a complex system and then you give up. Then you cannot do anything. So you have to look on subgroups, subsystems. So why to look on method complex system? Because we need, it's certainly that we could not solve the big societal challenges that are existing now, are unsolved. Economical problems are unsolved, and we cannot avoid ecological disaster caused by our own actions. So the problems are very strong, unsolvable, and we must find common properties in order to solve them. And mathematics can play an important role in this common property because it's the only one that can provide a unified methodology and coherent framework. Otherwise, it's totally heterogeneous and not clear. And it's also conversely, like it happened with computer science or with physics or with biology, complex system research poses many challenges to mathematics. So it's a two-way traffic. Some problems there arose problems that became independently mathematical issues. But the fact that we need mathematics is clear, but we need new math. The math that exists now is not sufficient to it. And these are the three categories that I classified the reasons, or the reasons for why we need a new math. It's we have In the socio-economical system, we have such large number of interacting agents of totally different character, like in parallel life. And the economists and finance are observing in the last 2 decades great conceptual change in the field. I mean, if we talk about no central banks, or we talk about the social platforms, social economy, everything is totally changing what we knew for 4,000 years of economics. And it's very multidisciplinary, because it's not only mathematics and stochastics and networks and physics, which is what we understand on one hand. There is also economics and finance on the other hand. So we need new math, which is generally more sophisticated mathematical models and more quantitative approaches, new quantitative approaches. It has homogeneity in networks and a lot of other mathematics that we need in. The field of complex system currently provides 3 types of sophisticated tool: conceptual tool, analytic tool, and computer-based. So conceptual, to think about the system, what is the system? Analytic for greater depth, and computer-based, we all take it for granted, to describing, modeling, and simulating the systems. So the first two, the conceptual and analytics, are mathematical tools. And there's, if I look only onto the analytic tools, then there are 3 types of analytic tools. 3 approaches to analytic tools. Many times you have to combine it. The first one is multi-scale hierarchies, that we have a group and an element of group as equal, for example. So you have to work this out. To understand how patterns of behavior arise from interactions, and of course the understanding of the process of formation that are changed, geometric and algebraic pattern formation, that's evolution. So it's multi-scale hierarchies, interactions, and evolutions. And all these phenomena, they're common to all complex systems, in particular the brain and financial market. So when you come to study a complex system, there are milestones to understand the complex system. So the first one is to identify the main complexity features that in the system that we are looking at, and then we have to have some strategy to represent the state of the system in a simplified way, reducing the overall complexity while keeping the distinguishing features of the systems, to have some kind of flexibility for the different systems. Then we need to describe the evolution in time. So this is something we do a lot in the brain, and it's very a symbol to many complex systems. But you don't look on everything. You selected some variables, so there is some choice. You selected some variables and you look how they represent, hoping that in number 1 of the identification, you selected the correct one or all of them. Then you have to look on the microscopic interaction among the entities. This can also be multi-scale. As I see, there are phenomena that we don't like in mathematics. And we have to validate the models to predict emerging behaviors. That's what physicists are usually doing. You know, they predict by some kind of intuition, but we have to validate it on real systems. But number 6, in some cases, you cannot validate on real system, and you have to suggest new perspective to interpreting what can happen without real system, real data to look at it. That's where predicting black swan is coming, or the next financial crisis. So this is the summary of the milestones, and I put in blue. If someone wants first time to look at a complex system and try to understand it, this is the slide to follow. And there are many complex systems that were not looked at yet. I'm not repeating it because I said it in the previous one. So these are the milestones, but now we have to look on the aspects that the mathematical model should consider when you are looking at those milestones. Now you want to introduce mathematics into the milestones. So these are 9 aspects that we need to mathematically model them. I explain each one very, very short. Each one, how does it get into the picture? So strategy is because the active particle usually use rational principle, but also irrational behavior. So when you do strategy, you have to consider both of them and the interaction between the rational principle that someone is following and the irrational one. Then the heterogeneity, because we have interaction among the particles, and there is the outer environment they're coming in, but many times there are learning abilities. So we know that there is a brain learning, there is a machine learning, but there is also system learning. The systems are changing. And this is for me the most interesting about this phenomena, that the system without having any guidance is learning. And then we have the everlasting change in social and financial system to have a personal benefit. So you never come to steady state. It's always changing. So equilibrium that originally we thought it would be steady state is not. And then you have non-linear and non-local particles. That's the non-linearity, because there are particles that have no physical contact. So you have to judge them when interacting on topological distance. Won't be a metric distance. And of course, we have to have games, because the particle strategy is view of uncertainty of the output, and also what we saw, the everlasting desire to benefit yourself. Learning and evolution, it's a Darwin-like selection that occur in many systems. And then space and networks, because the particles sometimes have fixed position and sometimes they move freely. So in that case, it's like the interaction, non-physical interaction, and also for individual particle, so we need more network topology rather than metric distance. And then we have the emerging behavior and the multi-scale issues. So we have microscopic scale and macroscopic scale. So the microscopic scale is the behavior of the individual, and it affects, of course, the macroscopic scale, but sometimes it's very difficult to understand how the microscopic scale gave the macroscopic scale. It looks almost autonomous. And there is, of course, we need a multi-scale perspective, and we need complexity reduction. So we mathematicians many times don't like complexity reduction, because we want something that is 100% sure or 100% correct. Physicists do it, and when I was a student, that's why I left physics. I started mathematics and physics. I didn't like this 90%, this complexity reduction. When you grow older, you see that life is not what you want it to be. So this is needed in order to study it. These are the aspects that we need, and from this aspect we have different approaches that should be involved. So we need game theory, we need all these that are here. And also on each of them, I see how each of them is coming into the picture. So each of these aspects, each of these approaches is having different individuals. So the game theory, it's players, and usually in order to find equilibria. But the new models, if we leave Nash out, the new models is coming to clustering of players, which is very, very human. And this was first applied to economical competition, but now is also used in biological and telecommunication interaction. And it's not really related, but I couldn't resist putting this picture because in the newspaper they say that Nash syndrome, he has no sense of humor and he cannot smile and he cannot laugh. And then I made him laugh. So the newspaper said she made him laugh. So I'm doing it here. Sorry. So I said game theory. Then we have agent-based model. This comes from computer science, but we are using it, and we have to make it mathematically rigorous in order to apply it. And usually it's the multi-agent system that we need to bound rationality and personal benefit in order to get something out of it. And this is used in networks and many systems that have a network structure on them. I mean, of course, the brain has the real neural networks are in the brain, but the artificial neural networks in the financial markets and in other places is, of course, it's very used. And then, we go to the population dynamics. So here it's interesting that many times the elementary entity is not one person, but the whole population. And you saw it that when governments decided about strategies for COVID, they looked at the growth of the population, the amount of COVID in a population. They didn't look at the individual. This is a super macroscopic attitude, but also studies show that many times you apply it to individual in interacting population. It also used in economics and finance, the population dynamic, of course, not only in biological places. And the next one is the social networks. In here, the individuals are called friends in the network, and there is the small world phenomena and the scale-free networks. And this is something that it used to be totally social science. When I was in the institute in Princeton for postdoc, my neighbor was a social scientist, and he talked about the strengths of weak ties. And then it became a basis for Facebook and to make him a very famous. And that started from the ties that people do in the institute. So he's the inventor of the small world phenomena. So I could give the institute this benefit. And then the artificial neural networks, they are computational models, and they refer to individuals as neurons. Of course, it's inspired by the animal brain, but the neurons. But we have artificial neural networks that are trying to imitate it. And the last one is the kinetic theory, and that the individual here are particle. So the interactions among the particles are described as stochastic games rather than deterministic. And of course, it's analog to the laws of classical mechanics. We have to see what mathematical fields are involved. So in principle, you can see all mathematical fields. If you need mathematics, when I moved from algebraic geometry, I realized I thought that there is in robotic. I started with robotic artificial vision and algebraic geometry were used there, but then I say I need to know everything in mathematics that one can imagine. So I wrote here the mathematic fields that are related, but of course there can be many other mathematics that you can. It's rather, I would say, all of mathematics, but you have to start with this one, with this list. So we move from milestones to aspects to approaches to fields, and math is coming immediately after you want to understand a complex system. Now I want to do a small focus on social system. And the reason that I want to do a social system, I mean, I say fintech. Fintech is social. So there is special challenge when it comes to a social system, because it's very much influenced, the assessment of the individual or the interacting is very much affected by state and strategy of other entities. So when it's influenced by other entities, it's difficult to predict, to understand what will go on with the individual. And then there is social competitions within nations. There is social competition that also is a little bit different. It's not there is no Darwin evolution that it makes some sense. You understand. You take trade-off. I want to have the wings should be bigger, but the weight should be lower. You have trade-off. But when it comes to social competition, it's different. And of course, the issue that the distribution of wealth has many models. But I mean, there's a cooperative and competitive trends. You can say market economy or communist economy, but there are different models for distribution of wealth. And also there are welfare policies that come in, and they can totally change, because sometimes they are not logical, they are not economical, they don't come in order to improve, they come for reasons that governments are putting welfare policies. And also there can be hypothetical government can decide on totally different wealth redistribution. So everything that we said before is not relevant if the wealth is redistributed. And the modeling approach should be developed to understand extreme events. And as I said, this is what I am interested in. But this cannot be predicted by classical. This cannot be predicted by classical theories. So, as I said, politics. We have politics in, so that's why social complex systems are more challenging. And I put it all for the financial market. And as I said, I'm interested in the black swan. So I took from the general the social system, I put together what you need for the challenges in the financial market. And just to sum it up, so it comes from strategy of other entities, from social competition, the distribution of wealth because of social interactions and welfare policies, and this redistribution for government action, and of course this extreme event phenomena that happened. And nowadays people say, well, I predicted 2008, but on ground it just happened. Okay, so I'm moving now from neurotech to fintech, and I say that I'm doing it via complex system. But what is the common phenomena? So in order to do it via complex system, I'm looking for common phenomena between financial market and the brain. And the brain has an overall unexplained collapse called an epileptic attack. The financial market has an overall unexplained collapse called 2008. So this is the way that through epilepsy, I'm studying financial markets. So from neurotech to fintech, I said via complex system, but specifically a black swan, which is epileptic activity. There are many more hospitals actually involved later in this, but I only put the hospitals that helped me to move to fintech. So what is epilepsy? Epilepsy is prevalent neurological disorder. It's much more common than you think, because there is 1% of the population that has it in some way. And sometimes you look at a person and for 20 seconds he disappears. He looks and he doesn't, and I think I'm boring him. So I said maybe I should say something. But he has a small epileptic attack, an epileptic focus located in an epileptic zone in the brain. And usually, if you have more than one attack, then they start give you medication. But in 30% of the cases, medication fail. And then you need a surgery in order to take out the epileptic focus. So you have to identify where is the epileptic focus in order to take it out. But surgery can be considered only if the patient has only one epileptic focus. So that makes it easier for mathematician, because from medical point of view, they already say there is a unique solution. So it's easy. It's easier. So when do we get into the picture? If the patient doesn't respond to medication, as I say, 30%, and it's not only that he doesn't respond, it means that the attacks, the seizures are very strong, and the attacks and the frequency is very strong, is very often, and that really makes quality of life very low. Even walking, many casualties in epilepsy is not from the disease, but from falling in the shower or something. So, and there are classical imaginary methods that were done so far, but sometimes they fail. And if there is no agreement between the EEG raw data and the MRI anatomical finding, and when they don't have agreement between the two, one says this and one says, then they use our algorithm to determine the epileptic focus and eliminate the need for a very invasive operation. Of course, you need the smallest that you can take in order to make less damage, cognitive and motoric damage. There was no FDA for this because it was like a supportive decision process for the doctors, because the classical imaginary method are with FDA, and then he takes it. So there are many hospitals in the United States that are using it. So the steps in localizing the epileptic focus. First, you have to obtain seizure measurements. That's the place where you need help from the medical staff. And then you do pre-processing, inverse algorithm, and compare results with pathology. Now, obtain seizure measurement is not easy, because if you do regular EEG, then there is a problem that the scalp is disturbing, actually doesn't give you accurate information. So before a seizure, before operation, the patient is put in the hospital waiting for attack. And they take off a bit of the scalp. It's not painful because there's no nerves there. And they put the electrodes on the brain itself. So when they put the electrode on the brain, there is no scalp disturbance. And then you obtain the measurement. But it's almost like EEG. It's recording the electrical activity of the brain. The question is, what does it record, how to interpret, etc. So this is the measurement, and then the pre-processing of the data. You get a lot of data, inverse algorithm, and compare results with pathology. So we developed 3 algorithms for the inverse function. The inverse function is mapping 3D electrical brain activity and finding the location of interesting phenomena, like epilepsy. Here you can also see, now I move to fintech. And we have 3 types of algorithm. It's a mistake. EEG, it should be. Types of algorithm on EEG and on underscalp. Genetic, analytic, and wavelets. And here I will only talk about the genetic algorithm. So obtain Caesar measurement, that's what you do, that's what you get when you are recording brain activity during the beginning of epileptic activity. So it's very, the synapses are very, very close to each other. It's almost that the whole brain is, sometimes it looks the whole, what you're recording is black. Usually when you record brain activity, you see synapse and then quiet and then synapse. And then here it's everything. It's like sometimes you see all black. But then you have to pre-process the data, clean noise using events contradicting the model, the original model, calculate amount of epilepsy for every electrode, and that's amount of epilepsy. Usually in a synapse you have the amplitude, how high it is, but here you don't do the amplitude of synapse, but amount of epilepsy for every electrode. If you have 28 electrodes, or you have 56, so 128, 256 is the most you can do in normal hospitals. And so the EEG of the event is also not characterized by a shape, because it's amount of epileptic, and elliptic source can be seen over relatively large time scale. That's also because the synapse is very short. Genetic algorithms are stochastic search. It's a search algorithm and stochastics, and of course they're randomized, based on the mechanism of natural selections and natural genetics, and it consists of 3 steps: selection, crossover, mutation, and then it repeats itself. So the crossover, you combine 2 points from the previous step into one point using a crossover rule, and you are left with half of the point that you had in the previous one. Then you do selection. You choose the T best points from the points left after the crossover, and then you mutate it, create new points based on points left after the selection process. So this is the flow chart. You have the start, initial population, you do some measure of efficiency, selection, mutation, crossover, need to approve, you go again and end. So more precisely in our case, you start the initial possible solution. So you choose M random, initial possible solution. Each is composed of n dipoles with an arbitrary location, orientation, and amplitude. Of course, you try to be clever in this, but it doesn't really matter. You repeat it so much that at the end it's clever. Interactive processes, in every iteration we will make the 3 following steps: the crossover based on brain geometry, selection based on forward equation, and mutation comes again on brain geometry. And the output is n dipoles that we believe that form the EEG measurement for a specific time step. And stability of the process, when the algorithm stops with only endpoint are applied to the forward equation. So there is a lot of randomness in this genetic algorithm. First, the first selection. We try to do the best fitted potential norm, but there is, we choose T best solution, so there is a choice. And we want to minimize the error from the original measures using the forward equation that the doctors were using before. And creating a new solution based on good solutions from the previous iteration by changing into a chosen orientation or using a step function or subset of the amplitude. So there is also choice here. And then the crossover, you combine pairs of solution from the previous iteration to make new solution. So there is a random weight average, so there's also randomness n. And the termination criteria is the stability of the process. So the choices that we make depends on few things, on the time frame of the epilepsy, on measurement properties, number of electrodes and the electrodes locations, on the head model choice, try to find simplified models that are not oversimplified for the relations between brain activity and scalp potentials, the source model choice, brain activity properties and noise. So I'll say, so the number of electrodes and electrodes locations. So the more electrodes you put, you get a better estimate. And when someone is sitting in the hospital for 2 weeks, then there is enough time to connect him to as many electrodes as possible. That becomes an issue, these electrodes, because the number of electrodes, and the better the hospital it is, will be a better hospital. I don't know how it came, but I have two collaborators that we wrote papers together. Suddenly the two kids of these two collaborators have epilepsy. I needed the hospital, so I tried to see in different countries where is the best hospital, but I also called my daughter and I said, take care of yourself. I don't know what happened when we wrote a paper on fundamental group. So you have to do number of electrodes and the electrodes location. These are the measurement properties that we are choosing. This is easy. Many times you start with what they had before. Okay, the head model is very important. We use 3 types of head models for our forward computation for the EEG. Layered head model, realistic head model, and geometric realistic head model. So what is the layered head model? The layered head model is assume that the brain is made of spheres, concentric spheres, and there is homogeneous conductivity in every layer. This is, of course, a lot of assumptions. I mean, we know the brain is not a sphere, but in order to do it, this is the model that, like we say, physicists can make it 90%, but it's less than 90%. Turns out less than 90%. I'll explain later how you discover this. So this is the conductivity for each layer. And then the layer head model, finally, it's an example, it's a lecture in mathematics conference, so finally there's a formula. So the formula for potential on the scalp depends on the number of layers and conductivity inside the layer and outside the layer. And disadvantage, of course, is that we use perfect spheres, which cannot cover all head areas. Even if you want to do a sphere and take out a little bit, it's even sometimes very difficult to put reasonable size sphere into the brain. It has to be a very small sphere in order to make it. The realistic head, unlike the layered head model, the realistic head model is doing segmentation. First of all, it has 2-dimensional realization, but we have also 3-dimensional segmentations with equal triangle elements, each with its own conductivity. So we are not subject to the layers, but we have some triangulation, which there's so much mathematics to work with it. So it was chosen just because of mathematical tools that we have here. And we have to interpolation of the measured conductivity between the different slices. And then we have a numerical solution for the forward computation. So the picture here, you have the brain in two sections of the brain that are perpendicular to each other, and then you have the triangulation on the brain. And then the geometric realistic head model, that's the one that we developed. It's 3D realization of the brain, obtained from the given set of MRI pictures. We took MRI pictures, we did image processing on the MRI pictures, and then we did corresponding to the shape of the internal surface of the brain. So I think that was extremely important in order to get better result for the operation. And this is of course, even when you do that, you still have, because there is no algebraic definition of the curvature of the brain, and in order to really understand, and when you calculate the amount of electricity that come to a certain piece of the scalp, you need to have three-dimensional real geometry, which seems to be like something simple. No mathematician can do it, but it wasn't so simple to do it. At the end, we took someone from that really learned in school number 2 a lot of space geometry, that and we figured it out. It's not. It seems easy. It wasn't so easy to do it, but that was extremely important because we were giving, because that made the difference. We took as much freedom as we could. So segmentation with no equal number of elements in each layer, with different shapes, not necessarily triangles, with resolution which do not depend on the other layers. And this was extremely advantage in order to get the best inverse function. But there are also other choices in the source model. The source model that represents the electrical activity recording. So there are few of them. There is the standard dipole source model, distribute source model, and improved source model. Of course, everything I do is green. We try to improve everything. But let's look at the regular one that we also used. So we look for the best choice of few dipoles position and orientation and amplitude. So we start with that. And then we try to minimize the cost function, matching the forward computation, the original forward computation of the current medicine, which actually we found out that sometimes the doctors even don't do that. They just look at the MRI, they look at the EEG, and decide that that's what we are going to do with their experience. And this was very frightening. Minimization of, so we want minimization of cost function. And the distribute source model, it's evenly spread fixed locations, but we look for the best choice of amplitude. So the model is looking to maximize its benefit in a different way. And there is noise. Noise is something in mathematics we like to ignore. There is environmental noise from the air condition of the building. There is additive noise on sensors, and there is brain. So the sensor themselves has some extra noise, and something is going on in the brain anyhow. When whatever you are doing, you're also thinking about something. So there's another activity, and also physiological motorics artifact like Acad. So the brain is also influencing it. When I first started to work on the MEG, on this certain machine that was a new machine, and it needed to be very, very isolated. So it cost $3 million just to build the room. So when you connect it, then when you are there, because it detects the magnetic field induced by electrical activity of the brain. So there's very low energy physics. So you had to make it very isolated. And we found something was amazing. So we were very happy. I went to the neurophysiologist that I consult always, one of the best in the world. He was very excited. But then we did another experiment and get the same result. So it was clear that then it turns out it's the air condition on the top of the building that gave that signal. So that makes me very know to be very careful. So there is the noise. So if we we take the same flow chart applies here with the modification, then we know that every element in the population is a possible solution. So mutation and crossover are based on the brain geometry and default fit method. Selection is based on the forward equation, and modification adapted to the time frame of epilepsy into account. So we tested the genetic algorithm on simulated data, and we did it with few choices, with different head models, with different source configuration, with predefined areas that in the brain, with event activity using average ERP trials, and other activities simulated with randomly chosen EEG segments. We use the forward computation related to the head model and calculate the electrode measurement. We add wide Gaussian noise to measurements, and signal to noise ratio is known and can be controlled. So we did all this modification. And at the end, we had 4 patients. We had big success in Michigan, in Chicago, in Los Angeles, and of course in Tel Aviv. And the comparing results, the results were in accordance with pathology. How do you know that you succeeded? The surgeon is taking the operation. So first of all, you have to make sure that you really used it and not in the last moment something happened. So that's it. But just by clinical, if at the end of the process, the patient has less attacks and less, not so severe, that's success. So it's only clinical that you know. So this was extremely successful, and there are more. When I wrote forward, at the moment there are more patients awaiting surgery. So we did genetic algorithm based on the default fit method, but we also did inverse EEG solution based on distributed source model, and we also used a wavelet and analytic algorithm. But here I only talked about the genetic algorithm. And it was nice to see all of them together. Okay, so from neurotech to fintech, how do I go? So the challenge is that to present trading and monetary exchange, etc., as a series of average synapses, and then advance notice and adaptation to the market time frame. There we adapted to the elliptic band and distribution of finding. That's also a challenge, because you have to be very careful, otherwise you will cause, if I say in 1 year there is 2008, then the prediction will materialize itself. It's like in physics, that the test is changing the result. So you have to be very careful if you're really only interested in academia, in the research. So you have to present trading, monetary, etc. as a series of average synapses that will look like that. This is the work to do together with finance people, with economists, and also with social scientists with inclination to numeration and to computation. Because which of the events, also in the brain, we also decide which of the events we are considering and which we are not considering. So also here you have to decide which event to take and which event not to take. At the end, to get something like that, and then apply on it everything that we did before, apply on it. So it doesn't have to be that way, but that's how you do it. And this is the end, and thank you for listening.
Questions?
Is epilepsy unique to humans, or has it been studied in other animals?
Yeah, you cause, it's sad, but you cause epilepsy to other animals in order to study it. But we do only on, what we did is only on humans. Not because I don't want to do experiment on animals. Of course, it's difficult for me to put epilepsy into someone, into an animal, but also because all this started as I want to show when I became manager of science. I wanted to show that mathematics is useful. So it's part of mathematics is everywhere. So I will do it on humans because that's where and it turns out to be useful in hospitals. So we were all very happy. Yeah.
Yes.
I just
Yeah.
have a question on
The
this side.
ladies first.
Yeah, okay.
I want to ask you, do you use neural networks in your study of epilepsy?
Do I use what?
Neural networks.
Not really. I mean, it comes into the neural networks comes into the genetic process. But in the wavelets, we do a little bit neural network, not here.
Yes, because I'm working in several neural networks and we do some prediction of the epilepsy seizures with neural networks.
That's prediction is extremely important
Yes.
as itself. I mean, for medicine, you need prediction plus localization,
Yes,
otherwise,
yes.
but for social issue, just the prediction is very important.
Yes.
Good?
Thank you.
Yes.
Yes.
I just want a more precise question about this dipole method which you use.
Yes.
To identify some dipoles. Is there any relation between the seizures, the location of the seizures, and the dipoles which you find?
Yeah, you do it because what you do, because the person that comes to operation already had epilepsy attack. And everybody around is trying different MEG or different issues, so they have approximately the area. So we have some advanced knowledge.
How many dipoles are necessary in this model, approximately?
We try to do as many as possible, so we did 128 sometimes. It's better to do 256.
Thank you.
Can you tell us a bit more about the genome of the genetic algorithm? And I also find it very fascinating that you went for a population-based heuristics for this problem, because the first rationale will be to go for something more trajectory-based, like variable neighborhood search or something like that. So can you please tell us why did you pick genetic algorithm as your meta-heuristic approach?
We didn't do only genetic algorithm. We did other algorithm for inverse function, you mean. What we did for inverse function, I said we did some analytic, we seen some wavelet. This just showed the best results. So you see, when the doctor is coming to, sometimes the regular ways are not working. So then you have to do something else. But how do we know that this worked the best? Because there was just one hospital that was willing, while they did the genetic algorithm, to do simultaneously the other one, measuring in the same, because they are doing it and immediately they're going to operation, so there's not much time. And it turns out this is the best. There's so much randomness, so maybe because of the randomness, and it goes again and again and again and again, then it becomes, genetic algorithm at the end works. We are here. We have some faults, but we are here.
Yes.
If we look at Dow Jones Index, it depends on the whole economic activities of the country, and this is very complicated system. Now we know the value of the Dow Jones Index at any second, and we can calculate the Hausdorff dimension of the graph, of the curve of the graph of Dow Jones Index. It turns out that is about 1.4. This means that the real curve is different from the smoothness. And it turned out that in the beginning of 20th century, the Dow Jones Index, the Hausdorff dimension of the Dow Jones Index is the same. This means that the random fluctuation and unpredictable fluctuation are the same in the end of 20th century and the beginning. It's part of the new mathematical methods for prediction the economy.
What about 2008?
What?
What about before the big crisis of 2008? You say the end of the 20th century, so that's 2000. What about 2008?
Dow Jones Index is known from the beginning of 20th century up to now. And
It's always the same.
House Dover dimension is the same.
This is, of course, very interesting, but it means that if this is the same and still we have collapses, it means we need another method, no?
But my question is, do you know the last value of the House Dover dimension?
No, I don't know it.
And how,
I will study, I will
what do you
learn.
think of this criteria? That's the question.
As I told you, I don't know it, so I cannot think about it. Of course, it's fascinating that something with all the changes that happened in the world in the last 100 years, this remained the same, and number of people, number of traders in the beginning of 20th century, numbers of traders and events now. I mean, it's unbelievable that it remained the same. I don't know, but of course it's interesting. I can learn.
All right, let's thank Mina once again for your and we resume at 11:30 with a talk by next week. Thank you.
Your neighbor was Mark Gramoveto? Your
Yes.
neighbor.
How do you know?
He is a pivot for my dissertation in consideration.
Yeah, we are very different.
I never thought I would meet someone that actually
I didn't mention the name now. I didn't mention the name. We were, you know, it started the first day, you know this place? The first day that we came to the institute, we came at 3 o'clock at night because that's how the light arrives. And they live all of us, and the walls are very, so they heard the people are coming, and they say nothing. And they thought, who's making noise in the kitchen? They didn't realize we just came. And then the following day, I didn't have staff, we didn't have a car yet, so I knocked on the door and I said, "Can you guys come in? Do you have an onion?" And they were shocked because no one is in America is knocking on someone else's door and ask for onion. But in Tel Aviv, we do it all the time. You know, neighbors are helping each other. So on that, he thought a lot.
It's extremely interesting.
Thank you.
I have
Thank you.
no
I
idea
appreciate that you
that.
came special.
But as a matter of fact, that's the first time I hear a talk of you. Can you believe it? We know each other for 20 years and more. And that's the first time I hear a talk. It was
All right, so we proceed with our morning session. It's an immense pleasure to introduce Ernesto Percio from Sindre staff, great scientist, humanitarian, and a friend of mine for many, many years.
It is. I like to say that my first Bulgarian influence was Ludwig. This is almost true. And, but I just will say that I'm extremely honored to be here. This was meant to be my 50th birthday celebration, but things didn't come to pass that way. But here we are, and my talk will be very light. It will be for the general public. It will contain no mathematics, and it will contain 0 equations, unlike Mina's talk that had 1 equation. Mine will have 0. But I hope you enjoy the ride. This is an expository talk. So when I say criticality, I mean the origin of life. I like to think of the origin of life as a critical moment in a process. I'm going to report on some research that my laboratory has made on understanding the origin of life. So these are all the people that have been involved in this research project. And you can see that it's very strange that there are no Mexicans in this team. It's 4 Colombians and 2 Russians that have been involved.
Actually, Estonian.
Estonian, that's right. Estonian, Russian, and 4 Colombians that have been involved with the development in this work. So, this is the laboratory, and now I'll go into the father of artificial life. So artificial life sounds funny, sounds science fiction, but it's actually a field of study. To put it in a moderate language, is models toy models, just like there are toy models in physics, string theory, and all these things. There are very simplified models that try to capture essential features of a phenomenon. Likewise, there is this very simplified model of life that try to capture essential models, essential features of the very complex phenomenon of life, but enough features to allow one to say sensible statements that can be sometimes very formalized in a scientific fashion, but that will give qualitative properties of various aspects of life. And today we will study the origin of life. Anyway, the mind that started all this was that of John von Neumann. He was born in 1903 and died in 1957. He didn't live too long, 53-year-old when he died. But by then he has transformed all of science. And so now the font is very tiny because this is the list of contributions of von Neumann to science. And I just wanted to put it in one slide, but it's almost impossible. Just the first one says, it's very far from you, but I'll read it. The first one talks about mathematics, and then just in mathematics, the first just dot. Bullet point is foundational mathematics, measure theory, functional analysis, algebraic theory, group theory, lattice theory, representation theory, operator algebras, geometry, and numerical analysis. In physics, quantum mechanics, hydrodynamics, nuclear physics, and quantum statistical mechanics. In economics, game theory and general equilibrium theory that already appeared in the stock. In computer science, the von Neumann architecture. Every computer you are carrying in your pocket today has the von Neumann architecture. Linear programming, numerical meteorology, scientific computing. And now in boldface I put self-replicating machines because it's important for us today. Self-replicating machines will be this model for life. Stochastic computing. Statistics, enormous amounts of contributions will fill the whole slide. He was a pioneer of the application of operator theory to quantum mechanics, the development of functional analysis, key figure in the development of game theory. He invented, together with Stanislav Ulam, the concept of cellular automaton, the universal constructor, the digital computer, quite a contribution for mathematics and science in general. And notice that both Turing and von Neumann were mathematicians, and they transformed all of science through their invention of the digital computer. Von Neumann published over 150 papers, and in what counts the secret classified reports, it's 200 papers. Of course, 50 of them were secret classified. So 150 published ordinary papers, 60 in pure mathematics, 60 in applied mathematics, 20 in physics, and the rest in engineering. And his last work was an unfinished manuscript entitled The Computer and the Brain, and again very related to Linstock, The Computer and the Brain. Then there was another work precisely about self-replicating machines and all this, but it was published much after his death because it was really left unfinished and people have to continue this work to publish it. In any case, his analysis of the structure of self-replication preceded the discovery of the structure of DNA. Although by the time he published the first ideas in self-replicating machines, DNA had been discovered. And there was this cryptic line at the bottom of the paper in the discovery of the DNA by Watson and Crick that says, it has not escaped our attention that this could be used to try to explain a mechanism for replication, but they didn't really understand the process. And although von Neumann didn't know of the publication of the structure, the double-helix structure of the DNA, he understood the process. So it's a fascinating history of the early understanding of self-replication in actual biology. In any case, now I will very quickly mention this paper by Marchal, Jean von Neumann, the founding father of artificial life, Because he makes a couple of very interesting points that I think are very important today. The abstract says, aside from being known for his contribution to mathematics and physics, John von Neumann is considered one of the founding fathers of computer science and engineering. Not only did he do pioneering work on sequential computing systems, but when he was trying to understand parallel computing is when he went into biology. But he also carried out a major investigation of parallel architectures, leading to his work on cellular automata. His exceptional vision and daring borrowing from biology the concept of genomic information, even before the discovery of DNA's double helix, led him to propose the concept of cell-reproducing automata. So he understood that information had to be digitized, that it had to be in a code, and the process by which this code needed to be replicated, everything before the discovery of DNA. So, among the contributions of von Neumann in computer architecture, he was the first one to propose that computers should have memory. Before that, engineers were doing a lot of work with cables. He proposed this was a fundamental contribution. Computers should have memory. And he introduced binary numbers into computer science. Before that, the decimal system was used in electronic computers. It was von Neumann who said we should use the binary numbers, 0, 1, 0, 1, 0, 1. It was von Neumann, the genius of von Neumann, who had this profound idea of using the binary numbers in electronic computing. He liked calling his invention, Gurulam, of cellular automaton, actually at the same time that they were making the A-bomb. At lunchtime, they invented cellular automaton to study life. So they developed simultaneously the technologies of life and death. And he liked calling it an interdisciplinary subject. This is words from von Neumann himself. An interdisciplinary subject lying in the intermediate area between logic communication theory and physiology. He was thinking very much about biology when he was inspired. He thought of this von Neumann architecture for computers as different organs of a living system.
It was the H-bomb, actually.
Well, when we did the cellular automata, they were doing the A-bomb. And then he, of course, had this idea with that Teller proved to do the H-bomb, of course. But this was at the time of the A-bomb, you know. In any case, and this is more or less the historical development of his ideas, getting to the self-reproducing automaton. His first question was the universal machine, and he understood the Turing universality. And what this means is just that the Church, the Turing thesis, and he understood this very deeply, that every modern computer, the computers that he designed, were all, they could do everything that can be computed with them. They are universal in that, and you see this everything in emulation when you play one game of one operating system and a different operating system, you are seeing this universality, where one machine can emulate perfectly another machine, because a Mac is universal, and a Windows computer is universal, and a Windows can emulate a Mac, and a Mac can emulate a Windows. This is the concept that there is this universal object of computing that can compute as much as can be computed in classical terms, without going into quantum computing, classical computation, mechanical classical computation. So there is this universal object of computation called the universal Turing machine, and this universality was understood very deeply by von Neumann. Then the constructing automaton, I'll go into that, the universal constructing automaton, and then self-reproducing machines. And I will, rather than describing this in words, I like pictures, because we're geometers. So I'll try to show a picture of these aspects here. But first, I like very, very much the beginning of this paper by Claude Shannon, the father of information theory, right after the death of von Neumann. Shannon, everybody that knew von Neumann, realized that he was extremely, extremely proud of his discovery of the structure of life. He thought of it as his major contribution. It was his last work. He was still working in bed about this when he died at the hospital. of cancer at a very young age. And he was still working on it, and he was extremely proud of this achievement. And all his friends understood too that this work was left badly unfinished, because nobody understood very well what he was doing at the moment. It took many years for people to start assimilating the ideas of complex systems that were discovered and conceived very clearly by von Neumann and all these things. Of course, he is one of the inventors of game theory, and he understood very profoundly what he was dealing with in his attempt to mathematize biology. In any case, von Neumann's contribution to automata theory. Well, he said, I love this paragraph. This is Claude Shannon. This is 1958. DNA was discovered in the double helix structure was discovered in 1953. But everything is very confusing. At the beginning, it's not clear. I mean, it's how the replication will come. It's still not understood the concept of gene. We still don't understand the concept of gene, and the way that proteins were synthesized from this, etc. It's very early on. And it says, Shannon says, the theory of automata is relatively recent, and by no means sharply defined area of research. It is an interdisciplinary science bordered mathematically by symbolic logic, and Turing machine theory bordered engineering-wise by the theory and the use, particularly of general non-numerical work, of large-scale computing machines, non-numerical large-scale computing machines, and bordered biologically by neurophysiology, the theory of nerve nets, and the like, as Mina was mentioned. Problems range from Gödel-type questions, and we will come back. Gödel's incompleteness theorem will play a big role in this story. Gödel-type questions relating to Turing machines and decision procedures, to questions of duplication of various biological phenomena in a machine, adaptation, self-reproduction, and self-repair. And this dream of the big last theorem of von Neumann is this machine that copied itself, that produced copies of itself. It wasn't imaginable. He worked for years on trying to mathematize this concept, and finally he did get it. I'll show it. Von Neumann spent a considerable part of the last few years of his life working in this area. It represented for him a synthesis of his early interest in logic and proof theory, and his later work during World War II and after on large-scale electronic computers, involving a mixture of pure and applied mathematics, as well as other sciences. Automata theory was an ideal field for von Neumann's wide-ranging intellect. He brought to it many new insights and opened up at least 2 new directions of research, at least 2 new fields of mathematics. It is unfortunate that he was unable to complete that work he had in progress, some of which is in the form of rough notes of unedited lectures, and for some of which no record exists apart from his colleagues' memories of casual conversations. In fact, he already had the correct program for the self-reproducing machine in 1943, and this is way before he could try it on a computer. He did it by hand. It's very impressive. Now, John von Neumann himself, anybody who looks at living organisms knows perfectly well that they can produce other organisms like themselves. This is their normal function. They wouldn't exist if they didn't do this, and it's plausible that this is the reason why they abound in the world. In other words, living organisms are very complicated aggregations of elementary parts, and he's understanding very clearly the concept of complex system, and by any reasonable theory of probability or thermodynamics, highly improbable. And this is going to be also very important for us. Living systems are systems that violate the second law of thermodynamics. That they should occur in the world at all is a miracle of the first magnitude. So how are you going to violate the second law of thermodynamics? Is the question that von Neumann asked himself. Well, he does it. He managed to do it. Here it is. He did it without computers. This is a computer-generated picture, of course. But he did it by hand. This is the code. This is like, you can think of it as the DNA of the machine that self-reproduces itself. He did. He got the code, He produces the machine that produces the machine that gets the code, that produces the machine that gets the code, that produces. He did it in 1940 something. Just by hand, without computers. And he had invented the whole thing. It's an enormous intellectual achievement. He had to invent the whole cellular automaton, everything. He just invented a new field of mathematics to be able to produce a machine that copies itself, and in the process he realized that he needed a genetic code. This is the first implementation of fundamental self-reproducing universal constructor. 3 generations of the machine are shown. You can implement mutations and draw here a little flower, a Snoopy, or Mickey Mouse. It's very nice. It's an extremely powerful universal constructor. It can construct any living being. It can construct any, however complex, living system, this object. The second has nearly finished constructing the third. So the second is constructing the third. The lines running to the right are the types of genetic instructions. Now we don't call them genetic instructions. He just had this code that he needed to do this. And which are copied along with the body of the machines. It's a towering intellectual achievement, this thing that he did in the 40s. Remember, DNA, 1953. This is 1943. So it's very impressive to say the least. So he has this model for life. And it's called artificial life. It's a toy model to understand life. Okay, but of course, we all know the guy that made this infinitely more approachable many years later. And that's the great John Horton Conway. Conway's game of life was an implementation of this fundamental idea, but that now every kid could play. You didn't need this tremendous understanding of the situation. And also happened at a time where computers were already available, unlike 1943. And now experimentation abounds by amateurs, and many theorems occur in Conway's game of life. So what is Conway's game of life? It's beautiful. You have this grid paper, infinite grid paper, and you of course have an eraser and you have a pencil, and you can completely fill one of the little squares or erase it completely, one of these little squares. And you think that it's huge paper and the squares are very tiny. And now you say that if it is filled out, this cell, so you have every square is called a cell, and if it is filled out, you say that it's alive, and if it is not filled out, you say that it's dead. You will say that. And now you say any live cell will fear that two live neighbors dies, as by underpopulation. Every live cell with 2 or 3 live neighbors lives on to the next generation. Any live cell with more than 3 live neighbors dies, as if by overpopulation. Any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. And there's this beautiful theorem of Conway, extremely beautiful with collaborators. Life is a universal construct, it's a universal Turing machine. Life is a universal Turing machine. It's beautiful, the theorem of Conway. Okay, so now...
Unfortunately, excuse me, he died from COVID last year.
I know he died from COVID. And he was a great friend of Mexico. He came many times.
Great lecturer.
We had lunch a few times. He was unbelievable, towering figure. But anyway, could you play the video? Now we have life in action. So what is it to program life? You have the big thing, and you specify some cells. You're God, and you specify some information. Cells that are alive, and then you run the universe with these laws that I described, and that's what happens. And if you're clever, then you choose very carefully the position of the cells that are alive. You choose them very... And look, this seems to be an entity that moves, but that has a personality. It's called a slider. And now, well, if you are really, really clever, and people are, believe me, they are, they will do anything if it can be done, then you put in very particular places your cell, your initial information. This is information. And of course, this is a state of low entropy. This is a state of low entropy. Once I put here the information, but there is something very off here. We're going to finish putting the initial information in the right place, and then a state of low entropy because I put the information in certain place. Think of it as the DNA. Think of it as the DNA. But now, when you finish putting the information in the right place and you just let it run, now we're going to let it run. Now we just put the information, and then all of a sudden you get all these sliders. And if you measure the entropy of the system, it just keeps going down. So this is violating the second law of thermodynamics. And this is very odd. So what's going on? Of course, it's going on that your laptop has a battery. And of course, energy is being pulled from the low entropy source of the battery of your laptop. But in the local system, the entropy is going down. Locally, the entropy is going down. And this is very odd. So, this is a realization von Neumann's idea. There's a very clever, extremely elegant realization by John Horton Conway. Can we go to next? Not the next. Now, just watch this video and tell me if you can feel in your blood universality. You should feel universality when you see this video. This is a life with initial information, just running. It's life, just running. And it's an enormous field of the game of life. We're zooming out because it's all these microstates, and we're going to see an emergent phenomenon, macrostates, thermal information. And you'll tell me if you are able to feel universality. We're zooming out. It's just did you feel universality? This is live program on live. Of course, if you can program anything, you can program live on it. And of course, I could keep going. I could program live on live, program on live. And at some point, I could just program a 16-bit Commodore 64 machine, an 8-bit Commodore 64 machine, which has been done. You can play any game for the Commodore 64 on live, because the whole processor has been programmed on live. So it's a universal Turing machine, indeed. This was programmed by Conway and collaborators. And let's go to the next one. But we just saw what it's called, next slide, sorry. We just saw what it's called an emergent phenomenon. You see, I could have programmed, not live, I could have programmed Grand Theft Auto 5 on live. I could have programmed Grand Theft Auto live. I don't know the names, or Minecraft, or whatever, on live. And then you could be in this reality that has all these phenomena. But of course, there is this microscopic level that you don't see. That is life, where it is programmed. And you would see all this, and you would feel the laws of physics in Minecraft, where some things fly and some things don't. And there is this laws of intuitive physics in Minecraft. But they would be emergent phenomena. They would be, you would be living on the matrix, literally. You know? So this is the notion of emergence. There is this phenomenon that macroscopically you feel temperature. You just feel temperature, but this doesn't exist microscopically. So it's an emergent phenomenon. Temperature is an emergent phenomenon. And so thermodynamics was the first science that understood this in a profound manner, and Boltzmann, of course, is a name that should be mentioned. But of course, this is so vivid in this field of cellular automaton. In any case, in philosophy, systems theory, science, art, emergence occurs when an entity is observed to have properties its parts do not have on their own, properties of behaviors which emerge only when the parts interact in a wider whole. And this is one of these properties of complex systems, emergence. In any case, can a machine program itself? So I want life, but the problem is that I had to put this extremely clever, to get these little animals walking, I had to be infinitely clever. I needed God to infinitely cleverly put the black dots where they have to be put, or you need von Neumann, which is God, to get all these sequence, and then get the machine that copies itself. Get the machine that copies itself. Can you not do that? Can you let the machine program itself and not know how to program itself, and yet have life? This is the question that we have to ask. Because we want to understand the origin of life. And we want to know how likely is that this happens. So we want a probability distribution for the origin of life. Okay, this is what we want. So, another property of complex systems is scale. Is this scaling, the so-called scale invariance of complex systems. So, this is a very famous example due to Siv and Mandelbrot, really. Mandelbrot and Siv. Siv was a linguist. And this is you take any book, any long book in the English language. And then you count, you take all the words and you make a dictionary of the words. You just list the words without repetitions, in alphabetical order. And then you count how many times the first word appeared, and count how many times the second word appeared, and so on and so forth. And now you put the word that appears the most here, and you put how many times it appeared. And the second word that appeared the most here, and you put how many times it appeared. And the third word, and the fourth word, and the third, and so on and so forth. And a long book typically has 10,000 words or something. It's an enormously large vocabulary, you know, an encyclopedia. And you count the words, and it turns out that you get this beautiful scale invariant law. Most words appear, 50% of the words in the book appear only once. And they do the heavy lifting. In fact, if you erase all the other words in the book, the ones that appear very often, you can still read the book and get very good understanding of what's going on. So that is to say, information is distributed, entropy is distributed according to scale invariant law. But this happens in thermodynamics where? Where do I know that entropy is distributed in a scale invariant fashion? Well, I already told you. Here. In phase transition in thermodynamics, entropy is distributed in this law. You know, the portions of enormous information are logarithmically distributed, you know, in this scale invariant law with respect to the portions of little information. The has little information, and we have very little information. I could erase it from the book and I could still read it. In fact, entire languages don't even have the words. But quality has much more information. So this is exactly the distribution of entropy in a phase transition in thermodynamics. But in thermodynamics, you have to fine-tune temperature, pressure, and volume to get to this state where you're having this phase transition. If you see water freezing, it forms a fractal instantaneously. And the fractal dimension is an expression of how far tail is the probability distribution, and a measure of the probability of rare events. Is the origin of life a rare event or a common event? Is the question that I'm asking myself. Okay. Is it a black swan, the origin of life? And I claim I'm going to prove that the origin of life is a black swan. Okay. And that's my theory. Very well. Anyway, heart rates of animals, well, there it is. Also the same story. So life seems to be in a critical state, but unlike freezing water where you have to fine-tune temperature, volume, etc., you have to fine-tune nothing, like occurs. So what's going on?
Can you explain what this graph means?
Which one?
This lesson, yeah, this one.
This one?
Or the previous one?
This one?
Yeah.
Yeah, I take the Quixote, a very long book. Then I make a list of the words. Then I count how many times the word animal appeared, 5 times. Then I count how many times the word, by the time I get to the T, I count how many times the word D appears. Oh, 10,213 times, many times. And I just graph how many times every word appears, ranking the words, not in alphabetical order, but in order of it, how many times they appear.
Okay.
But if I do that, well, I get this very hard to read graph. So I do it in log coordinates, and now it's a straight line. And this indicates this scale invariance, this fact that you're living in a thermodynamical phase transition state. Because this is entropy, and this is exactly the graph of entropy in a phase transition.
So you mean that this is the graph of...
Information, I am identifying information with entropy. Huh?
F log F? What is
P log P. Well, this is just, it's what I just said. It's just how many times the word appears, the logarithm of how many times the word appears, and the ranking of the word. And the logarithm of the ranking of the word, because from 10 to 10,000 is the same space as from 100 to 10. So I just do it in log axis, and it's straight line. And this happens in every language, for every long text. It's just a self-organized phenomenon. Sometimes language likes to live on a critical thermodynamical state. Language likes living on a critical thermodynamical state. Every language likes living there. Okay. Well, I'm starting to run out of time. This is nice patents in a city. You have a city twice as large. Well, you don't get twice as many patents. You get many more. For example, this is very impressive right now in mathematics. It's why one feels almost swamped by the mathematical developments of our era. Because if you have twice as many mathematicians, you won't have twice as many good films. You will have many more. Huh?
You mean like inventions?
This is things that you can count, patents. You know?
Patterns or patterns?
Patents.
Patterns, okay.
Yeah. Things that you can count in the office of patents registry.
Okay.
It's hard to count inventions.
Okay.
Anyway, so these complex systems like living in a critical thermodynamical state, but self-organized, not fine-tuned. I don't have to.
No, I think she asked whether this is patents or patterns or is that the...
Patents, patents, well, depends on potato, tomato, but yeah, is inventions in a sense. Okay, so earthquakes. You take the logarithm of the energy of the earthquake here, in the scale, Richter scale, whatever the scale, and you take how many earthquakes per year you have, and you get this. So the earth crust, and this is a beautiful problem in seismology, you try to write the differential equations for the earth crust and all these things using Newton's laws and Lagrange's and all these things. Unapproachable. It's extremely, and people try, and they are heroic. But you have this scaling. It's a tell. This is a tell. There is a complex system. There is in a critical thermodynamic state, but self-organized. You didn't do anything. Life, the earth crust, all the innovation, all these things put themselves in a critical state. They like being in a critical state, which is insane because systems like to get off critical states. But these ones just go and organize themselves from critical states.
So you want to say that the frequency, the earthquake frequency is linear?
Log. It's a scaling law.
Because
This is in log paper.
Because hurricanes are not.
Hurricanes are log.
No, they're not.
Well, no. We
I
can talk
think
about
so.
it, but
Okay,
yeah.
thank you.
Of course, in small regions, this tends to pay more. But even just in the area of Mexico City or just in the area of Istanbul, this is true. I think this is worldwide. But if you do the graph for the area of Chile, you get a very nice one, Mexico City. Anyway. So, physicists in the late 80s developed a mathematical model to understand. They produced the first cellular automaton that puts itself, that programs itself, that puts itself in a critical state. Unlike life, that I have to put it on a critical state by fine-tuning, this system puts itself on a critical state. You have to do nothing. It just puts itself on a critical state. And what is it? Well, you are to think that you have this huge table made of tiny square tiles, and that you put grains of sand on the tiles, on every tile. And every tile gets a number, the number of grains of sand that it has. Whatever, it's just the number of grains of sand. And there is, in this universe, there is time, discrete time. It's a cellular automaton, discrete time. The numbers are meant to be colors, many colors. And, but of course, the amount of the table is finite, say, and the amount of sand is finite, so it's finitely many colors. And there's only one law of the universe in this universe. If you have 4 or 5 or 6, more than 3, it's too unstable, it cannot hold so much energy, so it fires to the neighbor's 1, spontaneously. So this 3 becomes 4, this 3 becomes 4, it becomes 1, and it becomes 3. Just fires to the neighbor, because it had too much energy. And again, here it becomes unstable, so it fires, and this fires, we say it topples. So you imagine there is a pile of sand, and then if it is too high, it just topples to the neighbors. That becomes unstable. And it is an unbelievably beautiful theorem. That is very strange theorem, but very beautiful. It's fantastic for a kid, secondary school kid. That it doesn't matter the order in which you do the topplings, the final result is the same. And this is called abelian property. And the final state is well defined and it's stable. It's always well defined, and this is the final state of this initial state. Okay? And this is the cellular automaton. So what does this has to do with criticality? What does this have to do with criticality?
So the total sum is fixed?
No, because if you are on the edge, some sand falls off the table.
No, I mean, let's say you put the numbers in the grid. So do you assume the total number of that is given?
You have an initial configuration given. An initial configuration that is given. Okay. And could be low entropy or high entropy. Imagine that you start with a very large table and a billion grains of sand at the center. This is a very low entropy state. Very low entropy state. So you do it. Here you have a contact manifold, by the way. And This is the final state. So what the what? What the what? And physicists proved, in the physicist language, mathematical proof took 30 years or something, but the physicists proved, so physicists and mathematicians proved that this is a critical state. This is a self-organized critical state. You did nothing, you just fed it with low entropy, and it created life of itself. And these, you see some circles here, and they are the Apollonian packing of circles. This is a fractal.
But isn't there some Fibonacci?
Yeah, but there is more. There's of course Fibonacci because there is the Apollonian packing of circles. There is more. There's algebraic geometry. And all that was just encoded in this one law of physics, and a very low entropy initial state. And then you get life. You get a self-organized critical state. So I'm going to argue that in the modular space of Riemann surfaces, the very high genus ones are alive. I'm going to argue. So, let me... This is a fascinating field that we have been studying. It's beautiful. It's a beautiful field. Actually, these things form a group. These stable states, these critical states form a group. Actually, you could start with just a table and start putting sand at random, wherever you want. And sooner or later, you would start to get complex states. But sand falls off the table. So some states could repeat infinitely often with probability, positive probability, and some states would appear almost nowhere. So you ignore the states of the table that appears almost never. And you take only the ones that appear with positive probability. They're called recurrent states. The ones that appear, and it's an unbelievable theorem that the recurrent states form a group. But what blows my mind is not that they form a group. Is that it's the only group I know whose identity is highly non-trivial. This is the identity of the group. This is insane. It's the only group I know where it's nearly impossible to compute the identity of it. It's very hard. Is it so hard that nobody has proved that this square is here in the scaling limit? Nobody has proved that that square is there. You can see it all the time, of course. But nobody has proved that this square is here. And of course, it's very sought after conjecture. But nobody can prove it. In any case, this was discovered officially on July 27, 1987. And is the most cited paper in physics in all the decade of the 90s. The one that discovers these objects. So all of physics is the most cited paper in all the 90s for whoever likes these analytics. And they discovered that now you have this critical state, this huge critical state that blows your mind, and now you do the following. You throw a little grain of sand wherever you want. Bing. And it does something, or nothing. And you measure the size of the something that it did, or nothing. And you just have this, typically you have these little tremors. But then all of a sudden you put somewhere, I don't know where, somewhere, and you have this huge earthquake. And this measures perfectly the laws of seismology. But it's a cellular automaton, not a differential equation. Already Turing, in his equations for the tail of the cat and all these equations, the morphology, already Turing kind of understood, but it was von Neumann who understood that he had to write it in cellular automaton, not in differential equations. Okay. So, this is the only group whose identity is impossible to compute. Unbelievable. And it has scaling laws. These earthquakes on the sand pile. So, the physicists say that boundary identity, or this, is in a self-organized critical state. You have this thermodynamics. The information behaves like the thermodynamics, are a critical phase transition in thermodynamics, classical thermodynamics phase transition between water and ice, but it's self-organized. You didn't tune temperature, volume, nothing. You just did it itself. So finally, a model for life, you say. If you zoom out, you see tropical geometry. You see here CP2. You see these analytical tropical curves in CP2, complex vector space of dimension 2. And, well, you see them, you just see them. You just see them. So, we publish a paper in the Rosin of the National Academy of Sciences where we investigate this phenomenon. And I was very proud that the cover of the magazine was our picture. Was a very nice cover. So this is called the Teotitlán fractal in honor of the tapestries of Teotitlán, Oaxaca, from the native cultures. And of course, Oscar can say much more than I can about the issues of mathematics in traditional cultures. How do you call it?
The column you refer from India?
No. The field that studies the mathematics. Ethnomathematics. So, anyway, we call them the Teotitlán fractal. Okay, so this is the paper, and well, I put these two to point out that it's Kalinin, Guzman, Prieto, Shkolnikov, Kalinina, and myself. In any case, these does happen in nature, in the formation of semiconductors. This is well known. And so you have this pattern formation in nature that occurs according to the patterns of tropical geometry. These lines are called tropical geometry for some reason that I will not explain today. So that's what they are called, tropical geometry. So you have these lines, but some people would say, yeah, but this is not really alive. This semiconductor is not really alive. So, now we enter a little problem, the meaning of life. But I will explain to you today the meaning of life. So, it's complicated. It's complex. It's a complex system, isn't it? A crystal can grow, reach equilibrium, even move in response to stimuli, but lacks what commonly would be thought of as a biological nervous system or response or whatever. So these crystals that have this tropical geometry, there is a sector of the sandpile that is tropical. There is a piecewise linear sector of the sandpile that is tropical. And this was proved by Kalinin and Shkolnikov. So there is this sector that is tropical. So living things seem to be complex and highly organized. They have the ability to take in energy from the environment and transform it from growth and reduction. NASA defines life in the completely incorrect manner. NASA defines life as life is a self-sustaining chemical system capable of Darwinian evolution. But I said, well. I feel pretty much alive and I'm not evolving myself, you know. I'm not doing Darwinian evolution. I feel very alive. A little jet lagged, you know, and it's hard on me, but I feel pretty much alive. So I'm going to change the definition. And I had this definition, but Hilary Sean beat me to the punch on 22 April 2020. It's on my paper, and she just wrote this letter to a new scientist, and the letter says, giving me to the punch. Letters such as Bring Glover discuss how we should define life. Letters for April. Could we do so by considering what it does? Life exists in bounding systems, and it locally reverses the second law of thermodynamics by creating order or lowering entropy. Within set bounds, living things decrease entropy by consuming energy, which preserves the second law at a universal level as entropy outside the bounded system rises by more than it falls inside it. To accomplish this, life has highly complex ways of detecting and absorbing sources of energy, of self-repair, and of reproduction, making a clear divide between living and non-living systems. So for me, life is not going to be an object that is alive. Nothing is alive. It's a dynamical system that is life. It only occurs in time. So life does not occur for me at one point time estimates. As for the difference between a frozen hibernating frog and the dead frog that Glover raises in his letter, or a virus that is dormant in you, the herpes simplex virus that many people have and that sometimes arises in your mouth all of a sudden. As for the difference between a frozen hibernating frog and the dead frog that Glover raises in his letter, the frozen one has a readable information code within it so it can resume internally reversing entropy while the dead frog no longer has this. How about this as a definition? Life is a bounded system containing readable information code that can locally decrease entropy. That would be my definition of life. It makes no mention to Darwinian evolution. That will be a corollary, not a part of the definition, nor it has all these other aspects. And this definition, readable information code that can locally decrease entropy, doesn't mention chemistry. And that's good for me. Because I want to have life on universal Turing machines. Luckily for me, I did something wrong. No, don't play it. Luckily for me, tropical geometry. No, it's much too far in the future. Luckily for me, we'll see in the future that chemistry is a universal Turing machine. And that's all I'm going to use for about chemistry. All I will use about chemistry is that chemical kinetics is a universal Turing machine. And this has been proved. Okay, Langton Sand. There is this Langton guy. He was a great scientist and of enormous originality that never kind of had an academic job. He had a very tumultuous life, but that did many important discoveries, and he discovered many cellular automata of interest, trying to understand life. One is Langton's ant. What is so this is a nice story. Ludwig invites me to Moscow, so I give this talk about the tropical curves and the sand piles, and I'm trying to model life and the origin of life. I'm trying to understand this problem of Kuhn about the origin of life, and I don't know what to do. The space of the modular space that I have is too bad, both for Conway's game of life and for the sand pile. The modular space is too complicated. My computations explode in the supercomputer too fast. I can do nothing. I'm depressed. And then Bondal comes to me. And he comes to me in the hallway there at HSC, and he tells me, "Oh, have you seen this unbelievable Langton's ant? I have never heard of the thing." I said, "No, I haven't." He says, "Well, there is this question about the Langton's ant, blah, 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 blah." So I forget about it. We start working on chimeric dreams with Ludwig. But of course I come back home and it just hits me. This solves my problem. It has much nicer the modular space has much nicer properties than Conway's game of life or the sand pile model. So what is Langton's ant? Well, it's an ant. But the ant is not the life. Don't get confused. The ant is not the life. In fact, this is a dead state. There will be dead and alive states. So the ant is just a device to understand the rules. And there are some rules. 3 rules. Just like the game of life, there are simple rules. 3 rules, that's all. Very simple. So notice that when in the sample, when you have this fantastic picture, the fact that there is only this one rule in the automaton indicates that the Kolmogorov complexity of the information of the picture is very low. But there may be what is called computing irreducibility, where you have to go through all the computation to see the picture. There is no other way around. So while apparently the Kolmogorov complexity would be low, the program itself that does it, the Kolmogorov complexity, that's like Kolmogorov complexity outside of time. If you define some sort of Kolmogorov complexity with the shortest actual computation that you have to do, it would be very high. Well, so this is the answer. And it can go on and on and on forever like that. It has three rules, some rules, simple rules. If it is black, go to the left. If it is white, go to the right. Paint the thing black, if red, that kind of stuff. Very simple. Very simple rule. And this is what it was. So, Bondal's suggestion really paid handsomely. Can you play it, please? Play it again, son. So, and now this is greatly accelerated Langton Sun, and he's just doing nothing. As Bondal warned me, he said, first, you have to be patient. He just does nothing. You measure the entropy, it's very bad, just does nothing. So you start to get bored, you go here and there, you go for a coffee mug. So you count the steps, and 1 step, 2 steps, 2 steps. And then, at around step 10,000, not before 10,000. Could you move it a little forward? It's still doing its thing, nothing really. Nothing. Stop. Just pause. And then it hit me. This is not how Langton thought about it. Look, stop. Did you see that? Yes. Well, let me tell you what it hit me. This is the primordial soup. It's a universal. Langton sand is a universal Turing machine. So this is chemistry. It can model our chemistry. And chemistry can be modeled by this, by Church-Turing thesis. So it's a primordial soup. And then, bang, self-reproduction. But it takes a long time. And this felt so good. Now I have my model for the origin of life. This is not at all how Langton thought about it. But it's how I will think about it. And here is the origin of life. So right there is the origin of life. First you have universal Turing machine, primordial soup, long time, self-reproduction. But does this satisfy my definition of life? Well, it does. Although I have to very carefully define entropy, I have to consider just the right contact manifold in your language of just the result, because there is several options. So I have to just get the right contact manifold. So let's move to the next one. So you just saw the origin of life. I just showed you the origin of life. So, but no, previous one. But Gajardo, the people in Chile, el Centro para la Modelación Matemática del Departamento de Ingeniería Matemática, they proved this beautiful theory. Langton sand is a universal Turing machine, and therefore it can model all of chemistry. So it's a universal Turing machine. And so this is really the primordial soup, and this is really my origin. I'm really seeing a machine that programs itself. I'm really seeing a machine that programs itself. So, of course, people, and I'm going to kill myself because I forgot the authors of this paper. It's in the Mathematical Intelligencer. You can ask me. I'm so embarrassed I don't remember the authors. They encoded instructions for the Langton sand a little bit more complicated. And these instructions, I will call them the DNA. They don't call it that. I will call it that. And different DNAs produce different results. And this is the question that Mondal asked me. Nobody knows how to predict whether a specific Langton sand will stabilize. And he didn't know that they proved that this question is probably undecidable. It's this Gödelian situation. And why is it undecidable? Because of self-referential problems. So really Gödel's argument tells you that the decision problem for this, for the origin of life, is undecidable. These ones are chosen by the authors. They saw that this is stabilized, and you have the origin of life. You see? But if you take a random ant, in the modular space of ants, there is this big graph that you can think of it as a phylogenetic tree. So you have this phylogenetic tree of Langton's ant that is a tropical curve, and you can give it a metric and all that thing. So you take this tropical curve that is a phylogenetic tree of Langton's ant, then I give you a particular leaf on the tree, a particular thing, you don't know. And probably it's undecidable. You will never know.
So for those stabilized this rule, does Langton's initial rule known?
Sorry? Langton's initial rule, we know it stabilizes because we exceeded the stabilization.
Yeah, how about these ones?
All of these stabilize, look. This gets a tropical curve. This gets this beautiful pattern.
So they all start from the same rule in the beginning?
No. There is a phylogenetic tree of rules. There is a phylogenetic tree of rules. And so this new rule does this rule does this. You see? It's the simplest. Langton's is the simplest. It's like the origin of life, really. Because you can start mutating it, and you have this phylogenetic tree of rules, and then you have all this. But many genetic codes produce no life. Many. And it's undecidable. The problem of deciding whether this will produce life is it has this Gödelian self-reference problem. It's undecidable. Okay, so you get tropical curves, tropical analytic curves. So Langton's ant also knows all about tropical algebraic geometry. Just knows it. But I want to solve this problem by Kuning, that appears in his opus magnum, his masterpiece called The Logic of Chance. It's considered the Bible of theoretical biology. So I'm going to solve a problem that he proposes there. In the last appendix of the book, Evolution of the Cosmos and Life, Eternal Inflation, many words in one, Anthropic Selection, and a rough estimate of the probability of the origin of life, he does calculations. And then concludes that it's very small. That's 10 to the minus, that kind of thing. Very small, but he's doing a one-point estimate, and we mathematicians don't work like that. We would like to have the probability distribution and compute the moments of the distribution for the origin of life, wouldn't we? So that's what I will do. Okay? I'm going to use the fact that chemical kinetics is Turing universal. In both just chemical kinetical reactions and chemodynamical reactions with a formal language of differential equations. So both are Turing universals. So the primordial soup for me is a universal Turing machine. So this is a famous paper in Physical Regulators, 1997. Chemical kinetics is Turing universal. Remember, it just means that it allows for a universal constructor. It just means that it allows for a universal von Neumann constructor. And can you play it? This is our computation. We did these computations millions of times on a supercomputer, but this is classical Langton's ant. So we have these contact functions of the contact manifolds, and we have grows, kind of drops, like the market, you see, kind of drops, but grows, and in average is growing the entropy. The entropy is growing, and maybe you accelerate it a little. At the origin of life, see what happens. The entropy collapses. And so we program a neural network to recognize these patterns, we use machine learning. And now we took millions of genetic codes, ran them for a long time, because we don't know if they are going to stabilize, and computed the probability distribution for the origin of life. So I get the probability distribution for the origin of life, and ta-da! What do you know? It's a power law. So all the momenta are infinite. The expected time for the origin of life is plus infinity. So Kuhn was very optimistic, and he says so. I'm very optimistic. So God exists, and this is the probability. This is our result. This is our theory. This is the probability distribution for the origin of life. Origin of artificial life. But if von Neumann was right, there is universality, and this is the probability distribution for the origin of life. We will never really know that, but this is the best we can do. So we get this power law, this earthquake-like behavior. The origin of life is an earthquake of enormous magnitude. This is the probability distribution. All the moments are infinity. We discover synthetic viruses in this world. If we take, another thing for mathematicians. From this and my computations, I can conjecture, and now you put me in asylum, can conjecture that 66% of theorems in a formal system are undecided. And only 33% of theorems you can obtain a proof within the formal system. Because 66% of my ants never stabilized. Never, not never, but this suggests that there is a scaling limit. This graph suggests that indeed 66% of all mathematics theorems are undecidable. Who knows? Conjecture. And finally, we discover viruses. We get a very nice lantern ant that is very much alive, but then we kill it. So of course the genotype no longer exists, but there is these residues of the phenotype. Then we take a lantern ant that never stabilized, never. And then we make them interact, and the lantern ant that never stabilized magically does. It collapses the entropy. So it is this on that entity, not a live entity, that when it gets in contact with an alive entity, just takes life of itself. Just like viruses. So we discovered these synthetic virus systems inside this model for the origin of life. And that's it.
Just say that Ernesto is offering a course next week on an extension version of this, and so there is a bit more formulas. And so
more formulas. Here there were zero.
And so it will start on the 19th. I think it needs to be translated to the United States probably at 4 or 5 p.m. For more information, just look at the website of the center. You should start looking there anyway. So let's see if there are any questions to Ernesto now. Yeah.
Could you explain the graph, the last graph with X and Y? What are X and Y?
It is, remember the earthquake, the size of the earthquake, the energy of the earthquake, and how many earthquakes there were. Now I take all the ants, and I consider them earthquakes, but I take off the undecidable ones. I take 66% of them I don't consider. They just from this straight line in my graph like this, it's totally irrelevant, because they never stabilized. So of the 33% that stabilized, I asked myself the statistics of how long they took to stabilize. how long do I have to wait on a random planet for the origin of life that has the appropriate chemical, complex enough chemical soup? Because I need the chemical soup to be a universal theory machine. And then I get a power law distribution. But because of the exponent, all the moments of the distribution are infinity. So the expected time for the origin of life is plus infinity. So God exists. But not really. Well, I'm not saying that it does or it doesn't. I'm just saying that that Kuhn's calculation was exceedingly optimistic. That the distribution is extremely fat-tailed. And that it's really a major earthquake, the origin of life. This was to be expected, but I am offering proof. If you take certain axioms into account, like life is a cell-reproducing automaton in a universal theory machine of chemistry. This is compatible with the work of Jeremy England from MIT. He proves that life is unavoidable. And I said, yeah, it's unavoidable. The problem is the expected time is plus infinity. You win some, you lose some.
Another question. I always wonder, here what Gödel says, actually if the system is complicated enough, means it contains the integers, then it's possible to apply this construction of Gödel. Now, in the case of self-reproducing automata from Neumann, actually, what does it mean that the system is complicated enough?
You can do every computation on the integers. You can do every computation.
So that's the interpretation.
Every statement on the integers that can be verified by symbolic in a symbolic language can be verified automatically in this language, in the language of the automaton. Every automaton gets a language, and the decidable propositions of the language are automatons that end. That kind of thing.
I wonder about definition of life. So we have to have, it's also a question. We have to have a beginning, we have to have an end, we have to have some type of reproduction. What else do we have to add?
NASA adds natural selection. I don't.
NASA adds what?
Darwinian evolution. NASA adds Darwinian evolution. I say a frog is alive even if it's not evolving. I add local violation of the second law of thermodynamics. Local violation of the second law of
Is this
thermodynamics.
replacing the NASA?
Well, I am saying NASA is wrong. I'm saying I'm going to take away Darwinian evolution. I'm going to plug in local violation of second law of thermodynamics. But this woman beat me to the punch. I mean, it's in my paper, and this letter is from April 22. You know what I mean? It's on my paper.
I was wondering, is there any connection with the Penrose diamonds, or
Oh, yeah,
any other crystals? There are 230 varieties of crystals. Did you make some experiments?
17 symmetries for the crystals, isn't it?
17 in the plane.
Oh, yeah, that's right.
230 in the space.
That's right. You got it.
And that's why I'm wondering if you have used those crystals to see when they will become.
Well, as you know, Penrose crystals are undecidable. They are not algorithmically producible. So it is a fascinating question, and I don't think this is solved, whether there is a simple, there is complicated, of course, because of theory of universality, but the question is there a local model of complexity? Is there a simple serial automaton that produces Penrose tiles? We don't know. We know every one of these automatons produce them because of universality. But it's a very good question. I don't know. I don't know if there would be some DNA that would already start to have this fivefold symmetry. It was an enormous surprise to us that we could produce tropical curves. We know nothing. We know
It's
nothing.
very complicated.
We know nothing.
Yeah, crystallography is a very complicated, unfinished problem anyway.
We know nothing. Yeah, but it's a beautiful question. It is a beautiful question.
All right, so you'll have time to ask Ernesto more questions next week. Let's thank Ernesto again.
I'm asking
I don't
this.
think it has any problem if I take it off.
Yeah,
It's
it's
just a
not a
receptor.
memory, yeah.
Memory.
Actually.
I'm asking this question because I'm in Florida Atlantic University, by the way.
Fantastic.
And my students and I, several semesters already, 5 or 6 semesters, were investigating the symmetries in the world. So first.
Good afternoon. We are continuing with the outreach of mathematics. And the first speaker of the afternoon is Professor Steve Cantrell, the director of the Institute for Mathematical Science of the Americas in University of Miami. And he will talk on resources matching a spatial topology and evolutionary advantage.
Thank you, Nina. Thank you all. It's my pleasure to be here to celebrate the formal inaugural of the International Center of Mathematical Sciences here at Sofia, which has been a very valuable partner to us in Miami. So I'm very happy to be here. So today I'm going to talk about a body of work having to do with, as I say, resource matching and evolutionary advantage in spatial ecology. And so the background concept, of course, in all of this is dispersal. And so here I've given a nice little blurb about dispersal that I found on the internet here. And it's an ecological process that involves the movement of individuals or multiple individuals away from population in which they were born or to another location or for a population where they will settle and reproduce. One of the things I wanted to emphasize here is that there are many forms of dispersal that come into play, and that the fact that the conclusions about that I'm going to draw are going to be robust across a range of modeling ways that for dispersal gives some strength to what we're talking about. And so that there's natal dispersal that, for instance, when you have fish larvae that go out and then come back to where they would live later, or then adult dispersal, which is probably rather familiar to all, or then what's called here gamete dispersal, like seed dispersal for plants and such as that. So there are a good bit of points that I want to make about all of this to start as background. So resources and refuges are going to vary in space and time, and dispersal regulates who interacts with who and how. Then the outcome of that is going to determine, in the words of Lin-Manuel Miranda, who lives, who dies, and who tells the story. And so because dispersal traits then influence reproductive fitness, natural selection can act on these traits so as to adapt organisms to the spatiotemporal environments they inhabit. So that then one wants to look at the evolution of dispersal processes themselves. And so recent advances in observational techniques have improved our ability to empirically assess real environments and to describe and record the way organisms move through them. And likewise, as our modeling approaches and our ability to analyze them mathematically advance, we improve our ability to identify theoretical descriptions of what mechanisms produce what spatiotemporal patterns, and further, what patterns would be optimal if organisms were actually able to achieve them. So what I'm going to want to concentrate today is on aspects of this second question. It is clear all habitats are going to vary in space and time. They're going to be subject to external pressures, including human development and global change. And it's also the case that basic local demographic change can be modeled either as being density independent or density dependent, and given that density dependence, there are numerous modeling choices. So whatever particular point of view we take, we're only sort of scratching the surface, as it were. There's always going to be so much more to learn. So with that, I will take a particular point of view here, and for everything I'm talking about, I'm going to think in terms of local demographics as being essentially of logistic type, for which I'm going to mean an expectation that the local per capita growth rate, which is commonly taken as the surrogate for reproductive fitness in biological models, is going to decline monotonically with increasing density, and it becomes negative if the density is sufficiently high. So, and I'm also going to assume at first, through the first 2/3 of the talk, that environments are going to vary spatially, but are held temporally constant. Now that's clearly a gross oversimplification. However, I'm going to argue it's a natural first step for a couple of reasons. One, many environments can be regarded as varying seasonally, so adding temporal periodicity to the environment is the natural move towards a more realistic examination of the issue, and that the answer to the question of what dispersal mechanisms are evolutionary advantageous in temporally static environments is, as I suggested, is going to be robust across a range of mathematical modeling regimes. And these we now are able to extend in some instances to seasonal environments. So then this opens up even more interesting mathematical questions. And the key driver in all of this is how the dispersal mechanism in question is going to cause the distribution of the organism to match to the availability of resources. Okay. And so the approach here is to consider two variants of an organism that will interact with the environment at a local level in the same way. And we're going to we'll term those as ecologically identical, but differ only in their dispersal strategy, and we'll set up a model of pairwise competition. What we hope to identify is a dispersal strategy that can resist invasion by any other strategy, and that can in turn invade and replace any other strategy. And so what would happen, that would happen if the species employing what I call the dominant strategy competitively excludes any other variant employing a different dispersal strategy. And so by this I'm going to mean that the prediction of the model is convergence over time to the long-term distribution of the dominant variant, independent of the initial distributions of both the variants, assuming both are present. And because of my assumption here that we're having logistic type local dynamics, this will come down to three observations. First, if the dominant species starts out near its long-term distribution and the variant is introduced at low densities, the variant will die out. So that the variant is not going to be able to invade when introduced rare. And second, if the alternate species can achieve a positive long-term distribution, then the dominant species is introduced at low densities, okay, then its density will increase. And third, that there would not be a long-term distribution in which both species can be present at densities that are positive somewhere in the habitat in question. Now, the first two of these observations are going to reduce mathematically to the signs of principal eigenvalues of certain kinds of linear operators that we'll see in the discussion that follows. So, and so this is all in that, go back for just a second. This is all sort of here, because I'm looking pairwise and I'm doing competition and I've got the monotonicity in the local per capita growth rate. I'm in the context of monotone dynamical systems where this is going to be able to be carried out. Okay, so thank you. So let me review the history, sort of now that I have 10 years on from knowing some of this, so that I'm telling you a story. This was, I learned what I'm calling the first element after I learned about the second element. The first element I learned when I refereed the paper in question here. So, arguably the most interesting paper that I was ever asked to referee. So this has to do with what's called the reduction principle. And what it's going to assert is that in general, mixing or movement tends to reduce growth. And mathematically, this goes back to work on matrices in the 1940s by Samuel Carlin and other folks. And then there were some later very important contributions by Toshio Kato in his famous book in the 1970s and 80s. And the version of the result that I'm going to focus on is that of the paper titled Resolvent Positive Linear Operators Exhibit the Reduction Principle by Lee Altenberg that appeared in the Proceedings of the National Academy of Sciences in 2012. Here's his abstract. So, what he's talking about, the spectral bound S of alpha A plus beta V, where I've got a combination of a resolvent positive linear operator, something like a Laplacian, for example, A, and an operator of multiplication, which is typically going to represent something like fitness or per capita growth kind of term, was shown by Kato to be convex in beta. And then what Altenberger showed in a remarkably simple way, I mean, we're only using calculus, so it's very impressive, through what he called a dual convexity lemma, that this operator, or this spectral bound, this operator, S of alpha A plus beta V, is also convex in alpha. And notably, that the partial derivative with respect to alpha of this is going to be less than S of A. Okay, well, typically, movement doesn't result in growth. It just moves you to where growth then could become possible. Movement doesn't cause reproduction. And so typically then you're going to have this S of A less than or equal to 0, so that for diffusions with spatially heterogeneous growth or decay rates, greater mixing reduces growth. And so models of the evolution of dispersal in particular found this result when A is a Laplacian, or a second order elliptic operator, or a non-local diffusion operator, implying selection for reduced dispersal. And these cases are shown in this paper to be part of a single broadly general reduction phenomenon. So what he shows is that for all positive D, one of two things happens. So you've got S of alpha plus D times A plus V being less than S of alpha A plus V plus D times S of alpha A, or it's always equal. Okay, and so the first alternative then is the one where greater mixing reduces growth. So when we look then at models of the form, say, u sub t equal alpha au plus u times f of xu, for appropriate dispersal operators A and fitness operators V being f of xu, the alternative of the reduction principle, wherein greater mixing can possibly be advantageous, would occur if there was a vector u star greater than 0, so that a of u star is equal to 0, and f of x u star is 0. And when this happens, then the equilibrium is matching the resource distribution, and there's going to be no net movement. Okay, so that's the reduction principle part of this. And then the mathematical paradigm that we picked up, and I should say here that all of this work that I've done, and part of this has been in conjunction with my collaborator now of approximately 40 years, was Cosner, and many other people, and stuff. But this was the paper that is behind this whole train of thought. It was a paper by Alan Hastings that appeared in Theoretical Population Biology in 1983. And so what he demonstrates is that for reaction diffusion models with random dispersal and logistic growth dynamics, the slower disperser can always invade an ecologically identical faster disperser. So this is relatively simple looking model to look at. So U is going to be the density of a resident species moving randomly at a rate alpha in a domain and obeying this kind of equation, ut equal alpha Laplace u plus u times f of u in a domain with no flux boundary conditions on the domain. So there's no escape entry through the boundary of the region in question, and where the rate of growth, f, is decreasing with density. So crowding is reducing local growth. And so under very reasonable conditions, namely the integral of f of x 0 is positive across space, then the dynamics here will tend to a spatially varying positive equilibrium. And then if we introduce an ecologically identical variant at low densities moving randomly at a rate beta when the resident is near its equilibrium, the variant will be able to increase its density if and only if beta is less than alpha. And so here in this case, then the alpha A plus V would be alpha Laplacian plus f of x u star, and that will satisfy the first alternative of the reduction principle. Okay. And so then, about 15 years later, Dockery, Hudson, Mashaikow, and Komarovsky, in a paper in the Journal of Mathematical Biology, shows that if you consider a full competition model, I mean, Hastings' work only looked at a single equation, but if you look at a competition model here where the fitness term, the f of x u, is going to be m of x minus u minus v for both species, so that they're ecologically the same, and then they only differ in the rates of diffusion, again subject to no flux boundary conditions, then, and both species are present at the beginning, then the U will drive V to extinction if beta is less than alpha, independent of the initial conditions, so long as they are both present. So, I mean, Dockery et al. Are specifying the f of xu as m of x minus u, but the result holds in general. I mean, the key here is is having that m of x has to be non-constant. So you have to have spatial heterogeneity here. And so this is an example of one in which the first alternative of the reduction principle holds, and the diffusion at rate beta can competitively exclude any faster random diffusion strategy. The slower dispersal is going to win. They consider this problem for an arbitrary number of competitors, and they made some progress, but that remains something of an open question. Another collaborator, Adrian Lam, and I did show something about when diffusion rates, when you could have that the slowest dispersal would actually always win, but there's still more to do on that. But again, okay. So there's some key observations here. Random movement will never exactly match the background spatially varying carrying capacity. Okay, it's going to either cause it to overmatch in some places and undermatch in others, and the equilibrium in the corresponding logistic model, therefore, is going to arise through a balancing of demographics and dispersal, and not in the way that we can obtain the second alternative of the reduction principle. But what one can show using perturbation theory is that with a slower rate of random movement, the equilibrium that arises is going to become closer to the spatially varying equilibrium of the purely kinetic problem. This is where I call it equation number 6, ut equal u f of xu. Okay, and so what that means is that in essence, it's a closer matching to resources that leads to competitive exclusion. All right. So now I want to talk a little more about the story in the reaction, advection, diffusion case. So there are clearly numerous situations in which organisms have to move in order to survive. And so it is reasonable to expect instances in which higher rates of dispersal should be advantageous over lower rates. And the above history suggests for models in which dispersal and demographics are separate additive terms, and the dispersal is linear, one should look for dispersal operators where the equilibrium of the kinetic model is also in the null space of the dispersal model. Okay, and the evidence for the work of Hastings and then Dockery et al. Shows this cannot happen with purely diffusive dispersal. So since the discussion so far is focused on reaction diffusion models, let's take this as a starting point here. So some additional component beyond random movement is necessary, and a necessary place to start is to add advection up the gradient of the resource, okay, and at very, very low rates, that's not going to make much change. The slower dispersal would still win, but at low to moderate rates, it's going to be able to case that the advantage coming by moving up the gradient of the resource, so that you're queuing on it, could cause a reversal. However, in this process, once you start to Q on the gradient of the resource strongly enough, you tend to cause yourself to move to the very best places in the environment, therefore leaving space for the competitor to coexist with you. And in fact, if you look at the integral of the density, which would be the total population, that's going to tend to go to zero. And so we use the phrase. There are lots of problems when people talk about predator-mediated coexistence, which is something happens when you're looking in models of, say, a predator that preys on two competitors here. And so we borrow the phrase advection-mediated coexistence from this. This was in a paper with Chris and another long-term collaborator, Yuan Lo, who was at Ohio State. Then he's now at Shanghai Jiaotong University. So the question is, so the point here is that adding advection up the gradient by itself is not really what you're looking for to have something that's going to give you this kind of advantage over anything else. Okay, so, but what you can do here is you can modulate the speed of advection by advecting up the gradient of the logarithm of the resource, and assuming here, of course, that it's positive throughout the habitat. Okay, so that here the model you would look at is UT equal mu del dot grad U minus U grad log M plus U times M of X minus U in omega across 0 to infinity, subject to no flux boundary conditions. And then here we can take A to be mu del dot grad U minus U grad log M, and F of X U equal M of X minus U. Then U star equal M, that is the resource, is going to satisfy A star equal to 0 for any positive mu. And F of X U star is going to be 0. So this means that the second alternative of the reaction reduction principle holds. And what indeed in this case, a species following this, okay, will competitively exclude an ecologically identical competitor using a dispersal strategy B, where with B of U star not equal to 0. Now, you could perhaps come to a draw if you had one going at mu and another one going at D using the same pattern. But then that would be something that would give you a B U star being 0. But if it's not satisfying that, then you would competitively exclude it. And this goes back to Nina's lovely talk from this morning. She's talking about here, the dominant dispersal strategy has habitat scale implications. And even though at any locale within the department, within the habitat, it's only relying on local information. And so this strategy, there's something in the psychophysics literature called the Weber-Fechner law. This one, it says that the intensity of our sensation increases as the logarithm of an increase in energy rather than rapidly as the increase itself. So that saying that we process information in this way. And so how do we explain this? So there are three concepts sort of behind this phenomenon. And the first is not unexpected here. There's going to be notions of evolutionary stable or steady strategy or a neighborhood invader strategy that's borrowed from the adaptive dynamics. The second is a mathematical notion that lines some symmetry and its functional analytic generalizations for appropriate compositions of dispersal and demographics. And the third is an ecological construct called the ideal free distribution due to Fretwell and Lucas. It was published Acta Bio Theoretica in 1969, in which they were looking at the distribution of large raptor birds. And the two things about large raptors, such as eagles and hawks and such, is that they've got, among all animal species, they've got among the strongest abilities to sense the entirety of the landscape that they inhabit, and then to move freely within the landscape. So what the assertion here on that Fretwell and Lucas made is that when organisms can assess the environment perfectly, that's what they refer to as ideal, and can move freely, they will distribute themselves so as to maximize reproductive fitness. And so this is purely verbal ecological theory, okay? And my collaborator, Chris Klosner, in collaboration with a biologist who was a graduate student at Miami at the time, Murkesh Kshatriya, was among the first to formulate the ideal distribution mathematically in a PDE context. Now, an ideal free distribution does not necessarily involve population dynamics. So this is this nice little picture in the literature of fish in an aquarium, sticklebacks. And if you see here, they're being fed by Daphnia. And on one side, you've got a whole gang of the fish lined up, where the water, what's being dripped in, is a large supply of Daphnia. Whereas on the other side, you've got another slower supply, and so they sort of distribute themselves where they will each sort of get an equal share. And anytime I try to leave the parking lot at Miami International, I always think about this because I never am able to line myself advantageously. I always manage to get behind the slowest person. That's it. So fitness, as again, it does not necessarily require any kind of population dynamics. But what it will require is that the fitness is equal throughout all occupied locales within a habitat. Because if it didn't, something would move to improve its fitness. So, this would allow individuals to change their position with somebody else, but no net movement. But then if you take population dynamics into consideration, the equal fitness should be zero, otherwise everybody's going to continue to grow. So in models of this form, then what we found here in the case for the reaction, diffusion, advection, where you're advecting up the gradient of the log of the resource is going to correspond to an ideal free distribution. Okay, and as I said, this is robust across a large number of mathematical modeling formulations that then reflect different kinds of assumptions about how you're either conceiving space or time or both. And so such as reaction, advection, diffusion, integral, differential, and non-local, patch models, what are called metapopulation models, and models of natal dispersal, integral difference models, and matrix models. So, okay, so this puts us then now into wanting to be able to allow some degree of temporal heterogeneity in the habitat. So this was a paper that Chris and I published about 3 or 4 years ago here. And so the model is we're going to look at equation of the form, and I'm going to write it in one dimension, even though the results hold in higher dimensions as well. Of so where you've got u sub t being u ux minus u p of xt x of x, and then m of xt minus u in 0L across 0 infinity, subject to no flux boundary conditions on the ends. And here we're going to require mu positive, p and m to be smooth, and t periodic in time, and again where m of x and t is going to be positive everywhere. Okay, so it's well known, going back to the work of Hess and Laser, that there is a unique positive t-periodic solution to this problem that will be the global attractor of the model for all non-negative, non-trivial initial data. So it's a natural extension of the reaction, advection, diffusion results in to assert that the model is going to admit an ideal free dispersal strategy if m of x and t can be the periodic orbit in question. And the question is that possible? So in this case, if that were the case, then m has to satisfy this dispersal part, which involves both space and time now, and with the boundary conditions holding. And this would mean there would be no net movement when the population density perfectly aligned with resource distribution through space and time. Now the question is this in general possible? Okay, so here in one space dimension, p of x and t is necessarily a spatial gradient, so we can solve the first equation in the boundary conditions to conclude that p of 0t is mu times the derivative of log of m 0 to t. Then if we integrate the equation for m, we can solve for p, and we're going to need the resulting function to be t periodic in time, and we've got to match the second boundary condition. So the candidate then, this is then going to be p of x and t to be 1 over m times mu m sub x minus the integral over interval from 0 to x of m sub t of y and t dy. Okay, well, since m is t periodic in time, so it's p. However, in this case, now that we've got both spatial and temporal variance, the p is going to depend on non-local as well as local information. Okay. So if we set up to satisfy the second boundary condition, what that's going to lead us to see is that we would have to have the integral over 0 to L, the integral in space, of the resource, okay, to be constant in time. Now, this would require the total amount of resource be constant in time. This is a non-trivial constraint, but that's possible under plausible situations. So say if you had the resource peak moving back and forth in some kind of a periodic way. That's like reasonable, but it's very special. But in this case, a species then adopting this ideal free strategy, we can show that it would competitively exclude an ecologically identical competitor using a non-ideal free dispersal strategy. And it's a little work, but one can extend the results to higher spatial dimensions. So this is a reasonable start, but the condition is fairly special. And so there are a number of issues need to address in trying to interpret the idea of an ideal free distribution in when we are changing in time as well as in space. And so not clear what you mean immediately by individual fitness and how an ideal free distribution should be defined. And so using the local per capita growth rate as a proxy for fitness is inadequate in time-varying environments where the fitness of an individual depends not only on its location, but how it's moving through space and time. And likewise, in an ideal free distribution in a static environment can be defined in terms of habitat selection that optimizes fitness, but in a temporally varying environment, phenology, that is the timing of life history events, becomes important. So the setting we want to look at here now, sort of in general, is going to be this where I'm going to here for the local per capita growth rate is going to be in what biologists would call an RK form, where R is going to be sort of a local intrinsic growth rate. K is going to be the carrying capacity. Okay. If we had something like R was equal to K, then that would reduce to what I had just talked about. Okay. And again, no flux boundary conditions. And so the R and the K are going to be the environmental functions, and then mu and P are going to constitute the dispersal strategy. And these coefficients are going to be T-periodic in time, and they'll be smooth with R, K, and mu being positive over the domain and time. Okay. All right, so we need to have a notion of fitness in order to compare the fitness of individuals using different strategies. So let's go back and start with a model where there is a spatial location but no movement. So I'm at du dt being f of x t u times u. Then f of x t u is commonly regarded as a proxy for fitness. And so if I'm in a situation where f does not depend on time, and either u is held fixed, say, for example, perhaps at an equilibrium, or f does not depend on u, then I can interpret f of x u star, or f of x, as an average fitness at the location, and use it to model fitness. In the case of a time periodic environment, we can still define fitness at a location x via the period map describing u of x at time t in terms of u of x at 0. And what this would lead us to do in this case would be to set the average of f of x in t over 0t as the proxy for fitness. But now, and since we're interested in comparing fitnesses between individuals, and t is going to be fixed, we'll just drop that scale factor and use the integral of f of x and t over 0t as our proxy for fitness, so it should be, okay. So suppose now that the local per capita growth rate is still given by f of x t, and it's still t periodic. But the individuals do not remain at fixed locations. Instead, an individual will follow a path for t between 0 and t. Then we can take the integral of f of gamma of t and t over 0t as what we'll call a pathwise fitness f's of path, gamma. And so specializing back to the problem at hand, if the environment is temporally constant, so that R is R of x and K is K of x, the stable population will be at an equilibrium, so that the per capita growth rate depends on x only, and an ideal free distribution is realized when fitness is equilibrated, and it corresponds to perfect alignment with the carrying capacity. Then, if the environment is T periodic, we can expect population density to stabilize at a time periodic solution, so that the per capita growth rate is going to vary in space and time. This formula 16 here, R of x and t times 1 minus the ratio of v star to k. Then, if R of x and t is the same as k of x and t, we reduce back to the case we had before with k of x and t being m of x and t. So we recover the case when the total carrying capacity of the environment is independent of time. But perfect alignment is not possible without this assumption. And now, but we can now still get the notion of a pathwise fitness for this problem. So suppose the population were to achieve something we would call an ideal free distribution. Then we expect no individual can gain an advantage reproductively by dispersing itself differently within the time period. Okay, so the pathwise fitness should be equilibrated among all possible paths, so the distribution can be an IFD if and only if the corresponding pathwise fitness is independent of paths. And so then this motivates the following definition of ideal free distribution in this context, that then the population, if the population stabilizes at a positive periodic solution, then this is an ideal free distribution if the expression 16, if you go back for just 1 second, if this term right here, R of xt times 1 minus the ratio of phi star of xt to k of xt, okay, is then independent of x. And then what one can do then is get necessary and sufficient conditions in terms of R and X, whereby an IFD exists and is both an evolutionary stable strategy and a neighborhood invader strategy. And what this means then is that something that we identify as being an ideal free strategy will competitively exclude anything otherwise it's not. And so this then allows us to treat more general forms of logistic growth that you do, where you do not have to make the rather restrictive assumption that the amount of resource available in the environment is constant. We can allow it to depend periodically in time. And so with that, I think I have come to only one thing left to say, which is thank you for your attention.
much for this interesting talk. Connects to what you said and connect to complex systems, so it's a nice flow. Any questions? Yes, please.
Yes.
So your one of the main stepping stones was the assumption of density dependence for the growth and logistic growth. Have you seen anything in the literature that uses frequency dependent growth? And how if you can comment, like what are maybe implications for this theory?
There are other forms of ways in which it can be done in a reaction diffusion kind of case where you write out the dispersal, think of the dispersal terms in a slightly different way, and that will work. So this what I'm suggesting here is not the only way that it can work.
Because in general, for like the predator with multiple prey, there is always this question of how you actually describe like the response, and so yeah, there is a lot of discussion like whether you have like this calling 1, 2, 3, and how like relevant they are, what are the implications of those.
No, there is a little bit of work, a little bit that we've done on things having to do with thinking about ideal free relative in predator prey kinds of things. And currently I'm working with Chris and some other collaborators about situations where we would have, say, for example, an organism that would move differently, say, at a juvenile stage rather than at an adult stage, and so that then a single organism is represented by two equations, and so then we are looking at cases where we're looking about doing this pairwise invasibility kind of thing, where you're comparing two different things like that. Okay, and then there's also, you're back to the thing, you can, of course, everything that I have said, then suddenly say will become much more complicated when, say, for example, you would allow like Ali type dynamics, where you're no longer decreasing with this. I mean, the single thing here that is in common in everything is I've got a strong notion of monotonicity here going on, and so, but there is active work on all of these kinds of things, and in the reaction fusion infection case that Braverman and Korovenko did a different kind of dispersal mechanism as opposed to advecting up the gradient of the log of the resource, but one can make, in those cases, make a change of variables that allows you to move from one to the other. But
more questions? Okay, thank you very much. The second speaker in the afternoon is here, Viviv Shende. He will talk on reverse microchips.
Thank you. It's a pleasure to be here in Sofia. I've never been before. Let me explain what is the aim of this talk. Is it possible to close this one? So, if you have a Legendrian in a contact manifold, then I'm going to explain how to assign a sheaf of categories this is a sheaf of categories on lambda, and it depends on some piece of topological data, which I will explain. So this is somehow kind of old work. And then the new thing, but I will explain it. And then the new thing which I would like to explain is that if I have a complex Legendrian inside a complex contact manifold, then again I get a sheaf of categories. I said sheaf of categories. Maybe I should have said sheaf of stable categories. It's something like like derived category kind of thing. And so again, I get some kind of sheaf of categories. But in addition, inside of this sheaf of categories, so inside of here, I get a sheaf of abelian categories. Which has the same relationship to this sheaf as perverse sheaves have to do with the derived category of constructible sheaves. Okay, and you may notice that here I put this piece of topological data, and here I did not. That's because in this circumstance it won't depend on anything. And so why might you like to have you might like to have this for all kinds of reasons, but maybe the original motivation for me is the following. It's that if X is, so I wrote contact, but it's more or less the same to work with exact symplectic. It doesn't much matter, and so this is also exact symplectic. And in this exact symplectic case, like a complex exact symplectic case, maybe I should say examples. So X might be something like the Hitchin system, and lambda could be the nilpotent cone. We've had already some talks about Hitchin system and some discussion of nilpotent cone and so on. Or another similar example is a quiver variety, and somehow a Nakajima quiver variety in its core. Okay, and so you might, for example, be interested in knowing about the Sakai category of such a thing. And while by my work with John and Shiel, this thing, it's the same as microsheaves, the global sections of microsheaves on the quark. And in this instance, it doesn't matter whether you use this somehow weird or the complex one. And you might hope, so this is not quite true, but maybe close enough, that this is the derived category of the global sections of the perverse microsheaves. And the reason that it would be useful to know this is that by a result of by a result of Kashiwara and Volonin, this global sections depends only on the complement of codimension 3. Okay, so this lambda has maybe very complicated singularities, and this microsheaf category, which I'll explain later on, it becomes more and more complicated as lambda becomes more and more singular. But if you knew these kind of facts, then you throw away everything somehow in codimension 3, and this becomes somehow reasonable to calculate. Then you just take its derived category, and then you've learned this thing. Okay, so that's why you might care about why you might care about this. Okay, so that's where we're going, and now I will begin at the beginning. So at the beginning, I tell you what is a sheaf. I apologize to anyone who knows what is a sheaf.
Sorry, a question. So I want to understand the relationship between previous, the left blackboard and the right blackboard.
The left blackboard, the left blackboard.
Categories on the one hand. How does that relate to the equivalence on the right between Fukai and?
So Fukai category. It's a result of Sheil and John and myself that Fukai category of something like this, when this is smooth, appropriate kind, is equal to global sections of a certain sheaf of categories on the core.
Right. How is this how does that relate to the construction you announced?
This item is this item.
Yes.
And in this kind of complex case, this item and this item are not any different. And what I will explain eventually is that inside this guy sits this guy. What is true up to issues of like big and small and somehow infinite stocks and so on is this kind of thing. Yeah, that's how it's related.
I see.
So lambda is the core.
Lambda is the core.
Okay, so the upper arrow black on the left is your result of the geometry.
This is the result with John and Sheil.
Then I'm still not getting the relationship between the result and the arrow upstairs.
I'm just explaining that given this data, I will produce this item. And then given this data, I'll produce this item and this item. I haven't yet told you how I will produce that. Is it okay?
So kind of given X, you have the core, and then you construct the thing, and then you construct the smaller thing, and then you take the right category.
You said Kashiwara Vilonin?
Kashiwara Vilonin is some fact about microlocal perverse sheaves, and that fact is that they don't depend on anything in codimension 3. That's some kind of miracle. This fact is the fact that, if you're fortunate, the derived category of the heart of a T structure is the original thing. This fact is like 400 pages of mathematics. Is it okay, Dennis?
Okay, I'll make one last attempt.
Okay.
Suppose you did draw this squiggly line. Suppose
This
that,
is
suppose that you didn't mention it.
This is the content of the talk today.
Right. But it was not. It didn't appear in the formulation of this.
I mean,
the last line of the
this person is the same as this person.
Okay, so here it a priori exists. Oh, I see. Okay, gotcha.
Okay. Okay, so now I begin at the beginning. So what is a sheaf? Well, if you have some topological space, well, a topological space has open sets. Let's say U, V, and T open. Then pre-sheaf is something. Okay, first of all, it takes some value. Let's say take some value for each open set, and arrow this way. Yeah, okay, I apologize. arrow. You have restriction maps like this. Oh, I see. I had it right the first time. Like this. Or in other words, a free sheaf is a functor from, you take open sets of T, you take its opposite category, and you take values somewhere. So that's what a free sheaf is. And one important thing about such items is you can define something called the stock. So if you have some point P in T, then the stock is the limit. It's the co-limit of sections around. Okay. So that's what a free sheaf is. And maybe in case I should tell you this is what is a free sheaf. And then for such a thing to be a sheaf, it should satisfy one condition, which is the sheaf axiom. And it says that if I have some kind of cover of something, then somehow it's always going to be a map to the following limits. So this is the usual kind of check covering business. Okay, so this map always exists, and if this map is an isomorphism, then you get to be a sheaf. So that's what sheaf is. And the one important thing, so of course, any free sheaf, any sheaf is in particular free sheaf. Any sheaf is in particular a free sheaf. So this is an inclusion like this, and this inclusion has a left adjoint called sheafification, assuming that this category C is not good enough. So in other words, with any free sheaf, you can produce a sheaf. Now, in case you've learned what a sheaf is too long ago, you may not recognize this expression. The reason why we have to write this these days is that now we work with infinity categories. So when you do that, then you have to write like this. Okay, but all it means is that you can understand what the sections are on some open set in terms of the check coverings. So that's enough about sheaves, and now I'll explain to you what is microsupport. Okay, so now that was for any kind of topological space, but now we have to take M as a manifold. And I take a function from M to R. Maybe I take a point in M. And so given a sheaf, maybe even call this G. So given a sheaf, so after some sheaf, I'm going to define something which depends on G and the point P. And it's going to look a bit like a stock. But now, so it's somehow similar. The limit as U contains P of, now I make a cone. And inside here, I put, I can take sections on U. This is an open set and take sections. And I can restrict it to U intersect the pre-image of the negative part. G inverse R smaller than 0. Okay? So this is an open set, this is a smaller open set, I have a restriction map. Assuming I'm working in some kind of stable category, where someplace cone is defined, I can consider the cone. So this is, and that's the definition of this quantity. Let me give you a few examples of computing this quantity. Here is going to be this u, and my function g is just the projection to this axis, and I think this is r, and this will be 0. And so what am I supposed to do? Well, I should compare somehow. I should compare sections of the whole thing to sections on this part. And let's do 3 examples. So I could take the constant sheaf, which I'll just call z, and okay, let's take that. Let's take this point, P. So G, T. This is the cone between sections of the constant sheaf on this guy and on this guy. Those are both z's. So it's a cone z to z, and that is 0. That's example 1. Example 2 is I'm going to take something which is somehow the constant sheaf on the just this bottom part. So this is going to be g of z on g inverse of r negative, and then I'll put this g t. Okay, what is it this time? Well, this guy has no global sections, and I guess it does have. I've done a different example in my notes, but that's fine. It does have sections here, and so this is cone 0 to z, which is z. And let's try one more example. Let's do g inverse of r maybe non-strictly negative. G. Well, okay, how about this one? This one, it has global sections, and it also has sections here. And so this is again cone z to z, which is 0. Okay. So that's some examples of how this thing behaves. Oh yes, I don't need now the eraser. Okay. If you don't like sheaves, feel free to flee at any time.
So, you change the mark.
What?
Change the mark.
Yeah, this one. Okay, I'll try it. Okay, so now having done this thing, I can define the micro support. So it's something you associate to a sheaf, and it is a subset of the cotangent bundle of the manifold, and it is defined like this. It's pairs P, C, such that there's some function, like before let's call it G. There's some G such that dg P is C, so somehow its differential gives this covector, and well, this kind of microstock type thing I defined before, this FGP is not 0. And so it's like the support, except for this kind of thing, and you have K closure. So this definition and all that somehow an elementary theory of micro-support and micro-sheaf theory and so on, it's all due to Kashiwara and Shapiro. So this is the definition of micro-support. Maybe I give some just kind of examples. You can work out these examples for yourself, but here's some examples. F is locally constant if and only if the micro-support of F is contained in the zero section. And as one example, and the other somehow good example to know is a generalization of this, is that F is constructible if and only if the micro-support of F is constructible. I use for weakly constructible is conic Lagrangian, contained in. It doesn't matter. It is fine. A conic Lagrangian. And here is Lagrangian could be singular. And depending on your precise definition of constructible, you may need to say the word subanalytic. Okay, so that's two examples of how the micro-support, it tells you what kind of sheaf that you have. And actually, this micro-support came up in 2 talks yesterday. But let me just recall the example from Kenji's talk, because that was somehow, I should recall it. So in Kenji's talk, you had some space X, and you had some bundle E over X, and you had some function to R. And then he mentioned the following sheaf. You could take the inside E times R. You can take this is the sheaf on here, given by the constant sheaf on the locus where F is, let's say, smaller than 0. Okay, so I'll try it again. F of E is smaller than R on a point ER. Okay, so you can take this sheaf and you could push it forward. I didn't tell you what the push forward is, but if you know, you could push it forward. And what Kenji mentioned yesterday is that if you were to take the micro-support of this sheaf, this thing is the cone, and at infinity is the Legendrian generated by F. So I just mentioned that because we had it yesterday. Okay, so let's maybe I'll flip this one because it's not really relevant for the rest of the discussion. So now we arrive at the definition of microsheaves. So microsheaves, it's a sheaf of categories on the cotangent bundle, and you obtain it by sheafifying a certain free sheaf, and I define for you that free sheaf. So on some open set, you take the quotient. So U here, U is an open set of T star M. You take the quotient of all sheaves on M by. So I need a bit more space, but by the category generated by sheaves at sheaves with a property that their micro-support is in the complement of U. Okay, It's not hard to check. This is a pre-sheaf of categories, and then you sheafify it. And this is the somehow fundamental object of study of this book of Kashiwara and Shapiro. Although, because it was written before we had access to modern foundations, they never sheafified this pre-sheaf. But now we can, and so we prefer to consider the sheafification. So maybe I pause to take questions. Okay, so at this point we have a sheaf of categories on any cotangent bundle, and my task now is to explain to you, well, I promised you something which lives on contact manifolds, or exact symplectic manifolds. This is an example of an exact symplectic manifold, but it's certainly not all exact symplectic manifolds. And so now I have to explain to you how to use this construction to produce all the rest. I guess there's one last thing I have to do before this, which is so this it's a fact that so sheaves. It is obvious that like diffeomorphisms of M will act on sheaves on M. You just pull them back. What is much less obvious is that contact transformations of the cosphere bundle should act, because those do not in any way somehow have to come from the geometry of M. And so the following fact is somewhat surprising. So this is due to Diarmu, Kashiwara, and Shapiro. And I'll just state it informally. It says that contact transformations, transformations, they act on basically anything you want in this world, but in particular they act, so I guess with this attribution I should put isotopies, act on the microsheaves on S star M. S star M is a projectivization of T star M away from zero. Okay, and what is the proof? Let me explain to you the proof of this. So the proof. How do you get contact transformations to act on anything at all? And so the way is that like to a contact isotopy, you have to produce some sheaf functor, and the way you produce sheaf functors is you write an integral kernel. In other words, a sheaf on the product. So I called it and produce a sheaf on the product. And the geometric fact is that, so here's the product, here's the diagonal, and the geometric fact is if I have a positive small contact isotopy, has graph conormal to a neighborhood of the diagonal. Okay, so the graph, that isotopy, it's the conormal to this kind of things out here. That's a geometric fact. And then you observe two things. One is that there's an obvious sheaf with that conormal, whose microsporiot is equal to that conormal. You just take the constant sheaf on the inside. And the other thing is this book of Kashiwara and Shapiro. It tells you that the microsporiot somehow behaves well under integral kernel. So it follows that this sheaf I've told you here, it acts on microsupports by this kind of convolution with its microsupport, which gives you the small contact isotopy. And once you have all small positive contact isotopies, you just compose them and their inverses to get everything else. Okay, so that's why this theorem is true. So now that's the last ingredient I need to build this category in general. So now I take X a contact manifold. And I do something which should be very concerning to any symplectic geometer, which is I take a high codimension embedding. Into the cosphere bundle of Rn and n very large. Okay. Now why should this be concerning? It's because when you do something like this, you typically destroy all access you have to somehow the contact, the rigid symplectic geometry of this structure. In particular, such embeddings, they're covered by an H principle, which is why I guaranteed to exist. But to restore some kind of control, I ask, so I have this kind of embedding, this contact manifold, this is a contact manifold. I have the symplectic normal bundle, symplectic normal bundle, and I don't write the embedding in the name of the normal bundle because I take somehow as you take bigger and bigger, this kind of stabilizes. So I have a stable symplectic normal bundle. And I choose inside there, this doesn't always exist, but for the moment, let's assume it does. I choose inside there a Lagrangian, somehow a Lagrangian bundle. So this is what I call a stable normal polarization. And then I can now define the category of microsheaves. The mu sheaves X by definition is, this is some subset of the cosphere bundle. I have already defined microsheaves on a cosphere bundle in the previous page, and I can restrict attention to those with microsupport inside some particular subset, and so I take that. I take this microsheaves on this cosphere bundle, whose microsupport is in this Lx, and I just restrict it. Okay, and it is an immediate consequence of this theorem that this depends on the embedding only up to isotopy. If I have two isotopic embeddings, they get the same category. And it's a consequence of Gromov's H principle that, as you stabilize, somehow there's only one embedding. So this defines a unique sheaf of categories up to the somehow topological choice of this stable normal polarization. So now we have to discuss about this stable normal polarization. Here let me pause and remark, if you've ever seen, I've given you more or less the complete definition of this category. And I've promised you that this category for somehow appropriate exact symplectic manifolds by this long work with John and Shield, equivalent to a Fukaya category. If you've ever seen the definition of a Fukaya category, it takes a bit longer. Okay. So let's discuss about this symplectic stable normal bundle. Maybe first, this thing may not exist. Okay, like not everyone's stable normal bundle has a Lagrangian polarization. But if I have any x,
sorry, could you elaborate the remark you just made? This category is equivalent to the GPS's Fukaya category.
That's my that's the 3 papers of me and John and Shield.
This is contact management.
No. Okay. Let's discuss that at the end. Maybe I'll just say it. Okay, so if you take a Weinstein manifold, you can take it times R, that's contact manifold. Inside there, you can put the core, and now you can study inside this mu sheaves the full subcategory which is supported on the core, and then that's. So if I take any x, one thing which I can always do is I could take the Lagrangian-Grassmannian bundle of the cotangent, tangent or cotangent bundle of X. And so this is not going to be any kind of symplectic manifold, but this is. I take the bundle of cotangent bundles of Lagrangians-Grassmannians over X. Or, I mean, if this is contact, this will also be contact. You shouldn't put Tx, you should put the contact distribution. Yeah, sorry, I kind of, go back and forth between contact and symplectic, I'm not saying so. But you should put the contact distribution here in X of contact. Okay, so, but this one, it carries a canonical polarization. So, so always can define somehow without any choices at all a category of microsheaves, and I don't want to put it on this whole thing, but I'm going to restrict to the, I ask microspore to live inside just the zero section of this bundle. Okay. So this is some sheaf of categories. This is a sheaf of categories on the Lagrangian-Grassmannian bundle of Tx, or the contact distribution. And it has the property that it's locally constant in the Lagrangian-Grassmannian direction. And so now, if we want something which lives over X, we should discuss how to descend. Okay. So I guess without descending. Maybe I need to keep this one. So of course, a good circumstance would be if we had a section of this thing. Okay, but having a section of this thing more or less the same, maybe a section of the Lagrangian-Grassmannian, having a section of that thing is the same as having a polarization. And that's what we already discussed. So okay, so now we have to do some algebraic topology. The stable normal bundle, it's a stable normal symplectic bundle. It's classified by some map to BU. And the Lagrangian-Grassmannian of that bundle is classified by a further map to BU mod O. And what I have told you so far is I can define this category, or in other words, I have a section of this thing when this composition is null homotopic. But in fact, you can do a bit better than that. There's a map which is somehow some kind of universal microlocalization, which, so I told you that this thing, it's locally constant in this Lagrangian-Grassmannian direction, and that you can ask, what is the monodromy in that Lagrangian-Grassmannian direction? And somehow, to descend it down to X, I should be interested in killing that monodromy. And that monodromy is given by something which I discuss in a second, and that thing, the place it goes is to B2 of pick of the category of coefficients. And why does it go there? Well, here I've taken B2 of maybe a simpler map, which that's now more reasonable to think about map is the map of loops in the Lagrangian-Grassmannian to pick C. And why should such a map exist? Well, I told you this thing is locally constant in the Lagrangian-Grassmannian direction. So if I go around a loop in the Lagrangian-Grassmannian, I better come back to the same category. The thing is C-linear, so I come back to the same one, and its monodromy is an element of pick C. So that's why this thing classifies as this kind of map. There's a non-trivial thing one has to prove, which is that this map, it's map of infinite loop spaces. That's non-trivial fact, but let's sweep it under the rug. In any case, the theorem, which the additional content of which is this infinite loop business, this is due to myself and David Nadler, is that a null homotopy of this composite map X to B2 pick C. I think it's time for the new marker. The null homotopy of this map, it gives you a sheaf of categories. It's descent data for this for this one down to mu sheaf size. Okay. Now, there's one other thing to explain. So, okay, so again, it's X, du, B U mod O, B2 pick C. Now, if I have a Lagrangian index, then in a neighborhood of a Lagrangian, there's a canonical polarization given by a Lagrangian or Legendrian, given by just the Legendrian itself. And so this composite map has a canonical null homotopy. And if you use that canonical null homotopy, that amounts to thinking about like microsheaves on L inside of its own jet bundle. Then you get an identification of the microsheaves on L with respect to this null homotopy with local systems on L. But that null homotopy may be different from the restriction of whatever defining null homotopy that you have. Okay, so somehow, corollary of this theorem is that so given a homotopy. So maybe I'll give this null homotopy a null homotopy n. And then I put n. So this is this Maslov data which I mentioned before. Now I've given a homotopy of m restricted to L with that's somehow canonical. It's kind of canonical guy. You get an identification between mu sheaves L and the sheaf of categories of local systems on L. Okay. Okay. Now, what I haven't told, this stuff is all true basically without knowing anything about this map. Whatever this map is, that's going to be true. But to continue, now I had better tell you what that map is. So, so now it follows essentially from a result of Guillermo. He doesn't state this result, but it follows from results that he does state that this map mu. Maybe before I state his result, I should remind you that that pick of Z mod is Z plus B of Z mod 2. And what is this? Well, this Z is the shift of chain complexes. And this Z mod 2 is plus minus 1. Like the elements of Z plus minus 1. That's what this comes from. And so I should now describe for you what is this map. And there's a map. There's some maps which which are not so hard to describe. So U mod O, it definitely maps to BO at like point 1 O. And that one maps to B to maybe some amount of B's which B2 Z mod 2. So Okay, I don't promise I get the amount of B's correct. But this is the second Schiefer-Whitney class. And then there's another map from U mod O, which is the determinant squared. And U, after all, is unitary matrices. You can take the determinant and square it. If you come from O, that's 1. So this maps somewhere to S1, which is BZ. So this is not the theorem of Yermu. The theorem of Yermu is that this mu, theorem of Yermu is that this mu, in the case of when the category of coefficients is Z modules, is some maybe V of BW2 plus det squared. Okay. So he calculates it for you. And if you have seen the structures which you need to define the chi category, now you will recognize from here that the structure which is needed to define mu sheaves exactly the same. Because what you need to define the Fukai category is a null homotopy of this very same map. And moreover, what you need to do to a Lagrangian to put its grading is you can work it out that it's the analogous thing. So this should at least convince you it's plausible, this result of Sheila and John and myself. Okay, so that was the review of this old work. And now I have to tell you what I have just a little bit more to say about this, how to make this perverse T structure. Okay, and I think it will take one more picture. I have, okay, so I just remind you of a bit of I just write some groups, okay, so this is the unitary group. This is like some kind of, I think people usually call this symplectic group. It's unitary group with H coefficients. And this one also sits in O and R. And both of these sit inside SUN. I put square root to mean that the determinant can be plus or minus 1. And this one sits inside UN. Okay. Here's some groups. And somehow this is the structure group of the tangent bundle of a symplectic manifold. And so I'm for reasons of time, I'm only going to discuss about this part of this Maslov structure. And that's the part that's relevant to this perverse T structure. Okay, so this is the structure group that a symplectic manifold comes with. Dealing with the part of the null homotopy which has to do with this means that you have to reduce the structure group to this guy. That's because that's precisely what's killed with this det squared. Okay, so this is has to do with what's called a gradient. And okay, what are all these other ones? Well, if I were reducing the structure group up here, that's the same as giving a polarization. And here is some kind of quaternionic structure. I don't know what the official name for this is, but I'll call it that. This is the kind of thing which you automatically come with if you're a complex symplectic or complex contact manifold. And then, last of all, here this is some kind of complex polarization. So, the fact which is obvious from this diagram is that if you are a complex, here are two facts which are obvious from this diagram. The first is that if you are a complex contact manifold, you come with this grading part of the Maslov data, canonically. And then the second thing is, suppose I have L, this is a complex Legendrian, inside X, some complex contact manifold. Okay? Now, I want to discuss identifying local systems, somehow microsheaves on L with local systems on L, providing this kind of what I call secondary Maslov data. Classically, it's called giving a gradient of L. Well, in the neighborhood of L, you canonically have this thing, because you're somehow polarized by the tangent bundle to L itself. And therefore, that was the polarization which I'm supposed to match with whatever ambient Maslov data I've chosen in order to identify local systems on L with microsheaves on L. But the ambient Maslov data I chose just came from the restriction of this guy. And so, since both of those things come from this one, that gives me a canonical homotopy. So, I get canonical homotopy. It's not important that it's canonical, but you get a canonical homotopy for the grading part of a grading part of Maslov data. This kind of thing I've written before, and I won't write it, but if you want the rest of this Maslov data, that amounts to giving a spin structure on L. So what you get, at least let's say if L is contractible, you get a canonical isomorphism of local systems on L, sheaf local systems on L with microsheaves on L. Okay? And that means that given a, this thing, it comes with a T structure. I can ask, in what degree does my local system live? And so now I can define for you this perverse T structure. So, definition. Or I can define for you at least a candidate for this perverse T structure. So, okay, if lambda is complex Legendrian, then this mu per lambda, this is, I should tell you when is f in mu per lambda. This happens when, for every smooth point of lambda. Now, at a smooth point of lambda, I can apply this thing. F goes to, under this isomorphism, a local system in degree 0. And the theorem, that's the definition, theorem, and this is a theorem, let's see, it's in work with Laurent Code, my student Chris Quo, David Adler, myself. This is a T structure, which locally agrees with the perverse T structure. This is the heart of the T structure, the heart T structure, which locally agrees with the perverse T structure. I think that's more or less everything which I wanted to say. Although maybe it's worth, if you've ever seen the definition of a perverse sheaf, it's a bit complicated. And one way to read what I've told you is that this diagram is why the perverse T structure exists. Okay, so that's it. Thank
you very much. Any questions? Out of the questions during the talk. Yes, please.
So coming back to the examples that you had at the beginning, and you took the Hitchin system and the important cone, and so you get associated microsheaf.
So this is a category.
That's a category. Right, so you can do that for any Lagrangian, right? Lambda,
Yeah.
So if instead of taking the important cone, I mean, first of all, if instead of taking the important cone, you take some other Lagrangian,
like Hitchin fiber,
for example, or even defined by actually a real form, a complex group that those defined the moduli specific ones for those defined Lagrangians.
Yes, we'd also take that one. Yes.
Sorry.
Yes, we'd also take that one.
You can take it. So, can you compute? What happens? Can you tell what is that?
Well, I mean, for those like Hitchin section, that's a smooth object, and so the category of microsheaves is basically local systems on there. It's completely stupid. You could ask an interesting question, which is take an object of that category, and now I didn't discuss it here, but there's a functor which will, to an object of that category, associate to you an object on the nilpotent cone itself, and some kind of forgetful functor. And you can ask, what is the image of such an object? That's a very hard question. That has to do with this kind of Whittaker objects that Dennis talked about yesterday, and so on. So you can ask different questions. You can ask, take Hitchin fiber, and take object there, and try and push it to the center. What do you get? That's another hard question. It's a consequence of my work with John and Schild. You get something. And I wrote a very short paper explaining somehow this tautological consequence and what kind of thing you might get. What you get is what you might expect to be this kind of Hecke eigensheaf. But I do not prove it's Hecke eigensheaf. But you can prove some basic properties of it.
No more questions, then thank you very much. We'll meet in 15 minutes.
algebraic geometry, so I was stuck with the problem in topology. Here's something very basic, and it goes back a few hundred years if you think about it. So you can ask yourself, if let's say you have a graph, so G is a graph, and you want to say, okay, so I mean it's not a very sophisticated graph; it's just a planar graph. So a graph that embeds into the plane. Then you can ask yourself, well, how dense can it be? All right, so you have some vertices. All right, and then you can ask, well, how many? So these are some cities or whatever, some corners that you want to connect by streets, and then you can ask yourself, well, how many streets can you draw without having to draw an intersection? All right, and okay, so simple enough, you can just start. So let's say we want to be an efficient city planner, right? I mean, we don't want, there's no corruption here, we don't waste money on purpose. So there's no double, so we don't have an extra row, that we don't have like something really decadent, like a loop. So these things are not allowed. So this would be just a simple graph, right? Okay, so I can draw. At some point, I will be unable to draw anymore. Right, and maybe I can draw one more. One, two, draw this one more. Then I'm essentially done, right? I mean, there's no more I can draw. And now you can ask, okay, so observation is that somehow once you're stopped, once the city is at its densest, you observe that, okay, so the number of edges, the number of streets that you can draw is roughly proportional to the number of vertices, right? So in fact, what you get is that at most the number of edges is 3 times the number of vertices. Okay. I mean, you can make it a little bit better. So this is minus some integer, so minus some non-negative integer, and then that's not good. And the proof is easy, right? It goes back. I'm sure Euler or Descartes would have known this. The idea is that so you can use the Euler formula, right? Vertices minus edges plus let's call it a triangle is equal to 2. And what else do you need? Well, you need to have some kind of. So these are now 3 variables. So so once you draw every city, draw every street that you can draw, you see that every region is a triangle, right? It's bounded by a triangle. Otherwise, you could draw another diagonal. So what you get is also that so now each triangle contains 3 edges, and every edge is contained 2 triangles. So you have 2 times edges is equal to 3 times triangles. Okay, that's it. That's a simple formula. And then so from there you get to your equality. Okay, simple enough. So this is a few hundred years old. Now we get to a serious topology problem, and the nice thing that I want to tell you about is that really recent advancements in combinatorial algebraic geometry helped solve this, or kind of not only helped solve this, but they were necessary to solve this. There's no topological proof. So what is the natural question here? I mean, you sit in any math talk, you can ask if you start doing the talk, as I usually do, you can wake up at the end and ask what happens in higher dimensions. If you want to solve that always works. So a graph into higher dimensions, okay, that's trivial, right? So you can always embed a graph into dimension 3. Any graph you can embed into dimension 3. Okay, there's nothing going on there. But you can ask for a simplicial complex. All right, so simplicial complex is so for those of you who don't remember, it's just a collection of simplices such that each two simplices again it's a second simplex and so on. Right, so simple enough. And now you ask, okay, so you have a simplicial complex. Let's say you have a 2-dimensional simplicial complex, all right, and you want to embed it into some interesting space. it turns out that, if you want it to be like a very pure abstraction, you want a two-dimensional complex should go into R4. That's an interesting question. Because if you embed it into R3, well, you can look at the tangent space at each point, and then you get the planar abstraction there, plus you get the abstraction of faces intersecting transversally. So, it turns out that somehow this question you can basically reduce to the planar situation. So two-dimensional complex you want to embed into R4. And in general, the interesting question for this embedding is a k-dimensional complex, and you send it into R2k. Right? And now, okay, so what will be the limiting factor? Well, let's say this embedding is in general position, then if you fill in too many of the k-dimensional faces, at some point there will be transversal intersections. Right? Simple enough. Now you can ask, okay, so how many of these k-dimensional faces can you fill in? All right, so how many could you possibly get? And it turns out that, okay, so you can then try to use topology. You can use you can try to use some kind of Van Kampen abstraction for this, and try to get any useful bound for this. Right? So let's say you have two-dimensional complex in R4. How many two-dimensional faces can you have in terms of number of edges or in terms of number of vertices? And it turns out that the topology, at least currently, seems to be not well equipped to handle the question. So in particular, we don't know how to actually solve this problem, for instance, in the topological category. But if we restrict these maps a little, then we can use algebraic geometry. And the restriction is rather mild. So the restriction is just that your map looks nice enough. So here's the theorem. Actually, from 2018, and this is at if delta k. Let me write it in the more general version first. All right, so PL embeds into R2k, then the number of k faces. So I will denote this by fk delta. Is at most k plus 2 times the number of k minus 1 dimensional faces. Okay? Again, you can actually improve this by some additive constant, and so minus some positive integer. Let's not care about that. Somehow, asymptotically, this is times. You cannot do better. Okay, actually, this is somehow, if you think about it, if you're just greedy, like here, then you end up with examples that are essentially tight here. Okay? So this is the theorem in particular. Right? So if delta 2 embeds into R4, then the number of triangles is at most 4 times the number of edges. This is a nice generalization. All right. And that's a cool thing. The cooler thing is that this led, starting from this work in 2018, to a whole industry about not only developing this about an algebraic geometry or a Hodge theory that works without actually assuming positivity. So we don't have any positive structure, and we don't have actually the Hodge-Riemann relations. And I will kind of explain. I will try to indicate Hart-Lefschetz theorem that where you have no chance of proving the Hodge-Riemann relations. And instead, what I will argue is that we will replace these Hodge-Riemann relations, which say something about the signature of the Poincaré pairing with respect to an ample class. We will replace this by an idea that, for instance, also David Kazdan and Tammy Ziegler recently exploited. This is basically, we look at not the primitive subspace, we'll will explain what this means later. But we will look at we will look at sufficiently many ideals in our space, and we will say, okay, so the ideal on this ideal, the parent shouldn't degenerate. So basically, what we look at is if it's sufficiently many ideals, this Poincare pairing does not degenerate, this automatically implies a Lefschetz stat theorem. Okay, and I will explain how. Well, I will give you a sketch how. And by now there are 3 proofs of this fact. One is very hard and works in general characteristic, but there are 2 that work in characteristic 2 and characteristic 0 that are kind of, actually, I mean, the last one is like maybe a page. It's very simple. Okay? All right, so do I actually have to unscrew this or just rip it? Or okay, only be a matter of hours. Okay. Okay, this should be easier. So, first let me reduce this problem to the hard Lefschetz theorem, okay? That's it. So, Greta is already a little bit disappointed because I'm reducing it to a theorem in algebraic geometry. And the point is, don't worry, actually, we will give a combinatorial proof because algebraic geometry will not be enough, okay? We will give a combinatorial. Okay. Okay, so, well, I have my complex delta, right? Delta k. I embed this into R2k, all right? I can also just embed it, right? So I can just embed it into S2k. Okay, so that's just one compactification. One thing that is a little more complicated is to see that I can actually write this as a subcomplex. So delta k is a subcomplex of sigma, which is a triangulation of S2k. So this is a triangulated S2k. Right, so I mean, this requires a little care because you have to basically move the PL singular sets to the vertices. And then once you have that, you have to use a construction of being. The first step is slightly less trivial, but I mean it's okay. So it's a little PL topology. Okay, that's fine. So this is now a subcomplex inside my sphere. What can I do with that? Well, I can look. Okay, so if I have a triangulated sphere, and I talk to an algebraic geometer. Well, maybe he thinks about simplicial fans. Okay, simplicial fan is a collection of simplicial cones, right? And let me restrict to the case of where this fan is rational, so it's defined by rational vectors. And I also restrict to maybe the case where this is a complete fan, right? So it covers my ambient space, my copy of R. And I do this because, not because it's a necessary restriction, but because I can, okay, so I don't have to talk about the associated variety, but I want to talk about a certain ring structure associated with it, and the simplest definition is for this structure. So how is this related to a sphere? Well, I can intersect this fan with a unit sphere, right? And I get a simplicial structure in this unit sphere, right? So that's let me be fancy and use some color. All right. Wow. It's a 5-star hotel. Okay. So I get this. Now I get the polygon. Right. So
why can I assume that is rational?
Okay. If you have a simplicial fan, you can always assume that you can put the cones into a rational position. I mean, it's just perturb them a little bit. But the point is, okay, if it's rational, then we have a toric variety over this. And what I'm interested in is the cohomology of this toric variety. But now, forget this toric variety. Okay, so if you're an algebraic geometer, this is something that you can keep in the back of your head. I actually don't need the existence of this variety. I just want to write down the cohomology ring without ever touching the variety. I can do that. It's actually very simple. So let me first write down the equivariant cohomology. All right, and the equivariant cohomology of this fan. So I will just abuse notation, and I will think of sigma at the same time as a sphere in the fan.
Does it turn the right or left?
Yeah, even simpler. No, even simpler. Let's not even go to semi-rationally. So what I will do is I will just I will look at the continuous functions from this fan to, in my case, the reals for now. Okay, that are a polynomial on each of the cones. So cone-wise polynomials. So P of sigma is the algebra of cone-wise polynomials. Okay. Okay, this gives me a nice algebra structure, and of course it's graded, right? So there's I can speak about function those cone-wise polynomials functions that are linear on each ray. I can speak about those that are quadratic on each ray, or on each cone, and so on and so forth. Okay, so those are this is an interesting one, and this in fact, if you think if the fan is rational and you compute the equivariant cohomology of the associative variety, that's what you get. Okay?
So you don't need to impose any kind of comparability between the polynomials?
It's a continuous function, so they have to coincide on the arrays, right? So it's linear here, but it can have a breaking point here, but it has to be, it has to coincide. Okay? All right, and then okay, so I'm not interested in the equivariant cohomology so much as I was in the cohomology. So let me also write that down. So A of sigma. I will denote as P of sigma modulo the ideal generated by global polynomials. So this is now the cohomology ring, and in the case that it's actually a fan and it's a rational fan and so on and so forth. But I can do this in general. Okay. Note that there's some subtlety here. So this is a combinatorial object. I didn't give any geometry to it. Right? When I have a fan, actually, so a fan already has some kind of geometry. So this P of sigma, it turns out it does not depend on the geometry, but modeling out the ideal generated by the global polynomials, global linear functions, right, that's enough. This actually incorporates some geometry. There's some choice. I could give this is 1, 2, 3, 4, 5, 6, 7 gon, right? So it's a 7 gon that I drew in a certain way, but I could have drawn it in any other way. And this actually gives rise to different A sigmas here. This corresponds to choices of different Artinian reductions of this ring. So let me denote this by this choice of Artinian reduction by theta. Okay, this is my choice of global linear functions. Okay, so there's an entire space of cohomology rings given to a given sigma. That's all that you should take. All right. That's a simple enough ring. How does it help me? Well, I wanted to say something about some numerical invariance and some phase counting in delta. So let me first say some things about A of sigma. Right? Sigma is this larger thing that A of delta that delta lives in. Okay, so it turns out that so fact 1, and this is Hochster, is that A of sigma is a Poincare duality algebra. If you're a commutative algebraist or algebraic geometer, you might call this Gorenstein. Let me stay with topology. a Poincare duality algebra. And for now, I don't write this, this lower index theta, because it's not important. It will be important later. So here it does not depend on the choice of theta, so I leave it out. So meaning that if sigma of dimension d minus 1, then AD of sigma is isomorphic to my ground fields. I mean, again, later it will not matter what ground field I choose, but I mean, here it is somehow. For now, let me stay over the reals. AD of sigma, sorry. And somehow I have a perfect pairing between RAI and a D minus I. All right, so this is somehow, this is just my grading, right? So I said that it's a graded ring, so, and this, the ideal generated by the global linear function is a homogeneous ideal. So this is a fine way to think about the grading. Good. Okay? Okay. So in particular, in this case that I started with, right, I have this. I have a perfect pairing between, right, so AK of sigma and AK plus 1 of sigma. All right. What else can I do? Well, I can estimate the size of this space. So let's let me go back for a second. So let's say I would give you, oh no, just one too much. I would give you the task of estimating the size of A1 here. Could you give me a generating set? You see one? So I'm asking you to give me the generating some of the cone-wise linear functions, a basis for the cone-wise linear functions. You have an idea?
See the boundary devices?
Yeah. Okay. You have a combinatorial picture. It's you can just say it directly. Actually, what do they correspond to?
Number of grid.
Yes. But I mean, we have in this picture. I mean, tell me directly what they correspond to. You know, it's just a cone-wise. Okay, so for every ray I can choose a characteristic function. All right, so I take let's say I have this ray here, rho. I hope that is a rho. I don't actually. My Greek is not so good. I define a function that is linear and non-trivial here, and 0 on all other rays. And then I just continue linearly onto the domains here, onto the cones. All right? And that's, okay, so this is a characteristic function of that ray. For every ray, I get one of this function. And similarly for, okay, so if I look at, so the A1 is generated by the one-dimensional cone, so the zero-dimensional faces here. So that's more, a cone corresponds to a vertex in the sphere. And similarly, I can show that, the wrong direction, sorry. Magic. I can show that AK of sigma, that this is generated by the by the faces, by the simplices of cardinality k. So the dimension k minus 1. So this is the dimension of this. At most, the number of k minus 1 dimensional faces. And I wanted to say something about delta, right? So I can restrict this to delta, this ring. Right? So now what I do is I have my cone-wise polynomial functions, right? And I just restrict it onto the subfan corresponding to delta. Right? And the same bound holds. So dimension AK delta is just equal. There's no dimension here. K minus 1 of delta. Right? Okay, so this is, so that's one way of estimating the size of space. From above, I write down the generating set. Fine enough. The other way, if if I want a lower bound is, okay, so I write down a generating set and then I estimate the number of relations. Right? And I will do this somewhat cleverly already in the dimension that I needed. So I look at a dimension of AK plus 1 of sigma. Let's say that first. Okay, so I have again my generating set. All right, so I have my generating set, fk of delta. And now I estimate the number of relations, right? So now I'm rationally equivalent to 0. I have to think about what that means combinatorially. And this is a little more tricky, so it takes a little more time to find the right way of proving this. But it turns out also to be a nice and simple bound. So minus k plus 1 times fk minus 1 of delta. All right? And again, again, so this is sigma, but the bound extends in the same way to delta. Okay, minus 1 delta. All right, okay, so now I neatly connected all these inequalities here. I can go back to the inequality that I originally wanted to prove, right? I wanted to have an inequality between fk of delta and fk minus 1 of delta. And now it has become even more beautiful. I mean, it's hard to come up with an inequality that, I mean, we haven't actually proven it yet, but somehow, an inequality more simple. So the inequality that I want now is a better pen. Okay, so let me stack this black. Is that the dimension of ak plus 1 of delta should be at most the dimension of ak of delta. Right? That's the inequality I want. If I wasn't asking this question about delta, but about sigma, I would be done, right? Because I have this. This is a perfect pairing. All right. So ak of delta is isomorphic. Ak of delta, ak of sigma is isomorphic to ak plus 1 of sigma. All right, so if I was asking this question about sigma, fine, I can go home. But I'm not, so that's a little problematic. So what do I know? Okay, so well, I mean, if I want to show something like this, then what I want to show is right. I want to show that I have a surjection from here to here or an injection from here to here. Right? If I'm a combinatorialist, a topologist, or an algebraic geometer, that's what I want to do. So, okay, so I have my restriction maps that help me a little, right? AK of delta sigma to AK of delta, and of course AK plus 1 delta. And now, it's now inviting to say, okay, so I could just draw the commutative diagram here, but this isomorphism is like an indirect isomorphism, right? It's not a map that I can push down here. Okay, so in fact, if you choose theta not cleverly, then this inequality will be wrong. So you have to be a little bit careful. There's something that you have to say here. So now Lefschetz comes in. So Lefschetz says that this indirect isomorphism given by Poincare duality can be realized within the ring. All right? It's a property, it's not a theorem, right? In general. So Lefschetz says that this map here, induced by the multiplication with L, so Lefschetz property, property, it prescribes an L in A1 of sigma, such that this map here is an isomorphism. Right, but now L I can pull down to delta and I get this diagonal. And I'm done. Right? That's just the smallest diagonal placing that you can ever encounter. Well, I mean, not quite. You could have 3 terms, but fine.
So, but you have to choose this theta anymore.
Okay, so I mean, this is a property, right? Somehow, under which conditions do I have this? Okay, so now I could go to Philip, for instance, and ask him, well, what conditions do I need for this to hold? And it turns out that if I have this theta, if I have my fan chosen in such a way, right, if I actually correspond to a fan, and I have my fan chosen in such a way that it emits a function, a co-wise linear function that is special, so if it emits a convex co-wise linear function, then this corresponds to a projective toric variety, and I can use the hard left shade theorem. So here's the classical answer to this, and it doesn't give you a complete answer, but let me state it anyway. So classical answer. So when do I have this? When left shades? And it's like Twitter here. We have to restrict them to the number of characters because limited space. When left shades. So the theorem, if sigma complete fan then let's say, okay, complete fan of dimension, let me say dimension D, there exists an L in A1 of sigma that is strictly convex, so the class of a strictly convex function. So strictly convex does not mean, it's not the convex geometer strictly convex. It's a convex function in such a way that the domain of linearity of your function exactly coincides with the fan structure. Okay, it cannot be a coarser fan. Right, so linear. I mean, if it's linear already, or convex linear, that would be a big no-no for convex geometers called strictly convex. But I just require to break at the cones, right? Well, at the codimension 1 cones. That's enough. Okay. Then we have the following. All right. So then we have hard left sheds. And this is that. Right. I have an isomorphism between AI of sigma and a d minus I of sigma, right? That these are isomorphic, that's not a surprise, but I want that this is induced by the multiplication within the ring, L to the d minus 2I. Okay? And the second fact is that, well, this is somehow, it comes in tandem with something called the Hodge-Riemann relations. So Hodge-Riemann relations are the following. It's I define a quadratic form on the degree I part here of my ring. So I define, all right, so Q, L, I, this is a quadratic form on the degree I part. So AI times AI to AD. And this is, I take A and B and send them to A times B times L to the D minus 2I. All right, so now A times B is in degree 2I, and then I send it to degree D. All right, so that's it. All right, and actually there's a canonical identification. All right, there's a canonical degree map that that identifies this, so I can say something about the sign of this, the sign of this event. So this is somehow, okay, so this is a Hodge-Riemann bilinear form, And now, what does it say? So, I mean, there's no statement yet, right? I mean, Hart-Lefschetz just says that this form is non-degenerate. But what I do is I look at the primitive classes, EL, AI, and this is the kernel of AI to AD minus I plus 1, induced by the multiplication with D minus 2I plus 1. And now I can look at this form here on this subspace. Right? And the statement is that I'm definite, so this Q is definite of sine minus 1 to the I on PL AI. Okay? So you have the subspace, and you're just saying that you're definite of a certain sign on the subspace. Okay, and this is a marvelous theorem. It's kind of okay. So it tells us that if sigma comes from this complete fan structure, then actually I can answer this question, and I'm done. I could just go. I can go home. The problem is that you can actually make a quantitative argument that most delta will not embed into a sigma that comes from a complete fan structure. And you could be greedy and say, okay, I mean, why do I take a sphere, something homomorphic to a sphere, homomorphic to a sphere at all? Maybe I'm interested not in spheres, but homology spheres. So I want to embed into manifolds and so on and so forth. So you can get arbitrarily far away from this restriction of embedding into a sphere. And this year you will not, but the message is, even if you embed into a PL sphere, you have no chance of ever attaining this. You could think, okay, so I mean, there's recent advances maybe showing that Hodge-Riemann relations and Hart-Lefschetz hold beyond this kind of restricted setting. But it turns out it's okay, so my colleague June, he got the Fields Medal for this last week. And it's marvelous technology, but the point is, in this setting, you cannot hope for Hodge-Riemann relations. They will not hold. So this bilinear form, okay, you can write it down for general sigma. But the statement about the signature will just not be true. Most spheres will not satisfy this, just as a small. There will be no theta that you can choose. Okay? Okay, so I should have written this theta, this is with respect to this special theta. All right?
Can you write the statement that you're currently saying?
What?
Write that. You're saying that in some settings something doesn't happen.
Ah, okay. Okay, so you can show that the following statement. Theorem, and this is, you could get Goodman and Pollack. And Alon. So what they say, okay, so they even look at the most restrictive case of sphere. So the PL sphere. Okay? Is now the statement is that, okay, so most PL sphere sigma, so let me say it like this, so given D larger equal to 4, most PL spheres, meaning that, okay, so I look at all the PL spheres with a given number of vertices, all right, so on n vertices, cannot be realized as convex fans, or complete fans even. complete band. Okay, so you cannot even write down a complete band like that. Now you could ask, well, could there be like a theta where for some miraculous reason I still have the Hodge-Riemann relations, right? So notice that if I have the middle pairing, so if I have an odd-dimensional sphere, then I have this pairing of right, so a sphere of dimension of dimension 2k minus 1, then I have a middle pairing, right? So I have a pairing of a case of Hodge-Riemann relations where no L is involved. Okay? And you could ask, well, maybe for some miraculous reason, I still get the Hodge-Riemann relation. I still get some realization with the right index. But if you look at this argument of theirs, right, so then it shows that most spheres you will not be able to arrange the right index in the middle pairing. That's it. You have no chance of attaining this. Okay, so that's okay. So I mean, okay, so we don't have a chance of using the Hodge-Riemann relations. It's fine. But we can still use actually the Hodge-Riemann bilinear form. And so now I will state the theorem, the first theorem in its most basic form. So I will give you the hard Lefschetz for these simplicial spheres beyond positivity. So without the notion of Hodge-Riemann relations, without the notion of convexity here, and I will. I actually don't know how much time I have left, so I wanted to go into some
15 minutes.
15 minutes. Okay, so then those of you join us at the beach will get to. Okay, so I will show. We will go basically to much more general cases of integral semigroups, and in particular for Vignesh, I mean, we will go to mirror pairs and lattice polytopes. Unfortunately, you are not coming to the beach, but I think maybe they're also recorded, so you can see me in bathing shorts giving the talk. All right. So what's the theorem? So theorem, and this is Lefschetz without convexity. Ample classes. Here, the strictly convex functions. If you're an algebraic geometer, you call them ample classes. Right? Okay. And so here's the theorem. So sigma, I will restrict actually to the case of spheres. There's a statement of a manifolds, but then this A ring is a little more complicated to define. So sigma is a K homology sphere where of dimension d minus 1. It's a triangulated sphere. It's a triangulated manifold that has a homology of a sphere. It actually just needs to be a homology manifold, but it's fine. Of dimension 1, where and K is just any field. Let me for simplicity assume that it's infinite. Is an infinite field. So this actually, I don't make any assumption about the characteristic. Okay, so here you can. I don't care what characteristic you put. Doesn't matter. Then what can I do? So for theta generic, we have the following. So theta generic and L in A1 of sigma with respect to theta generic, we have first of all the hard Lefschetz. Right, so hard Lefschetz property. I will just write it in the following way. So that's AI of sigma and A d minus I of sigma times, this is the multiplication with L to the d minus 2I. This is an isomorphism. And now this theorem does not come alone. It's not, I mean, Okay, we don't have any hope for Riemann relations anymore. I mean, now for Wiener, I'm not even in characteristic 0 anymore. There's no way I could say anything like that. But I can go a little more of the Deligne route and say something still about the pairing that doesn't say anything about the signature. So this is the non-degeneracy on subspaces. So let me give the first of all Laman relations. Okay, so I still have the same bilinear form here. Okay, so what do I want to with it? So I want to say that this bilinear form does not degenerate. So then QLI does not degenerate at ideals. Okay, so these are basically these correspond to torus invariant ideals. So let me just say these ideals are of the form. I look at A sigma, and I look at any subcomplex delta, and I look at this restriction map, and I look at the kernel here. Okay, so I look at the restriction to I mean, for commutative algebras, it's just a square-free monomial ideal inside A sigma. Right? Okay, so maybe I should have written this on the next slide. And I don't degenerate at this subspace. Okay. And this is the 2018 form. And now let me also state something that is this is 2021, and there's this was originally by Papadakis and Petrotu. And then there are new proofs, 2022, which are very simple by myself and Papadakis and Petrotu. Now, so now I said, okay, I don't degenerate at certain subspaces. Now, Papadakis and Petrotu, they had this idea, okay, I look at this not over the fields that are given, but I look at this over function fields. So, let me give you the statement briefly. So there exists a nice transcendental extension, K tilde, of K. Yeah, of my field. And I should say, okay, so, sorry. Characteristic of K now is equal to 2 or equal to 0. Okay, so it's a restriction. It does not work quite in this generality, but it says something beautiful more. And so I have characteristic 2 or 0. There exists a field extension, and theta and L over K tilde, right? So I now define the coefficient system with respect to my field extension, such that Q L I degenerates as no ideal. I mean, no ideal just means, okay, so it doesn't degenerate the principal ideals. In other words, Q L I of U is not equal to 0 for all U in AI of sigma. Okay? Okay, good. So, as I said, at the beach I will say a little bit, I will say something about the proof. Maybe the proof, these are also recorded, so for those of you who miss it. And the proof techniques that go into this. I want to just finish with a remark though. This theorem is kind of orthogonal to maybe not orthogonal, but it's not a superset of the classical Riemann relations. Meaning that there are classical varieties that are as beautiful as you could ever want them, which don't satisfy this principle of not degenerating at subspaces. All right? And this classical variety that everyone likes and knows It's just a product of projected lines. So careful. Okay, so I could look at P1 cross P1. Right? It doesn't get nicer than, okay, so the projective space, but I mean, the next example in the textbook is P1 cross P1. So what fan does this correspond to? Well, I mean, it corresponds to just the fan over the quadrangle, right? Okay, so now I have, this is my fan sigma, right? I mean, if I think about it, my sphere is the quadrangle here. And I could look at delta given by the subcomplex here. This is delta, right? This is my subcomplex. And it turns out that if I look at this ideal, so the kernel of A sigma to A delta, then this ideal is generated by, okay, so now I don't have another color. It's generated by the characteristic function of this ray and this ray. They don't pair with each other. So multiplication is, I mean, this times this is 0. But if you think about it, this times itself is also 0. So what you're going to do? So the statement is, well, I mean, okay, so you chose the wrong theta. Right? So if you pass to the reducible surface, so if you just deform this a little, right? So if I take this, not have this, and then I have maybe this, then actually the Hodgman, this Hollerman relation holds. So why can I say this with confidence? Because actually the criterion is rather simple, in at least for one-dimensional spheres. As soon as you see that no two of these rays are collinear, this principle holds. It's a simple criterion that you can make. And that's it. Okay, so now in this case, okay, so you see that smoothness and projectiveness doesn't really imply anything about this non-degeneracy of subspaces, but you can always perturb to such a situation. And I think probably I should finish now, right? I have 5 minutes. Okay, let me go to the questions. Okay, I think it's better. Thank you. Yeah.
Were there combinatorial proofs of the classical or toric result?
Yeah, I mean at least in the case of toric variety. So all these proofs that combinatorial Hodge theory that somehow proves Hodge-Riemann relations, like for the water conjecture or for the Kashtan-Lustig conjecture before, or even there were even works before that. They use basically one combinatorial proof due to McMullen. So that not Curtis, Peter McMullen. So he gave a combinatorial proof of the Lefschetz and Hodge-Riemann relations in the case of toric varieties. Okay, he created this kind of valuation algebra, which actually turned out to be equivalent to this algebra, and gave a combinatorial proof. And every single one of the proofs that in combinatorial Hodge theory basically uses principle, this proof idea. Yeah.
Okay, thank you, colleague.
Could I ask a few more questions?
Sure.
Very elementary though, but I couldn't understand first my question. How you connect algebraic variety with the conal possibilities?
Sorry,
fan over synthesis.
Okay.
Okay, so could you please explain to me, because I know a little bit about atomic constructions, etc.
Yeah, but I mean, then you know that how you get from a rational code to a fine toric variety, right? Yeah. So now if I have a sufficient fan, then I group together these fine toric pieces.
So I thought this is
For every cone, I was trying to write. Along the cone structure, I do them together.
This understand. Initially, how you do all of this if your cones are not partially, if they are not.
No, okay. No, I'm not. Okay, I should say, I'm not actually doing I'm not actually looking at the variety. I find this really also
What do you mean by variety?
I don't have to, I'm not working with variety at all. I have the